welcome to this roundtable session here at our Digital Autonomy and Computing Continuum. Before we start and before I give the floor to your moderator, Rolf Riemenschneider from the Commission, I would just give you a quick heads up regarding some rules in this meeting. And for that, let's have a look at them together. So this is our overview of our speakers. Rolf will say something more about this. And before we start, I would like to remind you that this session is being recorded. If you are not a speaker, please stay muted and keep your video off to save some bandwidth. This is an interactive session, so we would like you to engage. If you would like to say something, you have the possibility to raise your hand. You can find the button when you hover over the screen. It will appear left next to the red leave button. So please raise your hand if you would like to say something, and we will give you access to the stage then. If you have any questions or comments in the meantime, please make sure to use the live discussion chat. If you cannot see the live discussion chat, please go into full screen mode. So you have a button there saying full screen. If you enter that, you can see the discussion. And if you have any technical issues or something like this, please go to the help desk. You can see it in the menu. And now I give the floor to Rolf, who is your moderator for today. Rolf, floor is yours.
Many thanks, Verena. Many thanks also to the CSA, EU IoT, and Cloud, and so on to support the event. So a warm welcome from my side as well. I'm very happy to be your host or the moderator for this session. I would like to share my screen. Oh, no, please. Did it stop recording? See participant share my screen. Screen one, so you should start seeing something.
Full screen yet? Down left corner, down right corner, yeah, somewhere there. Okay. I think you don't see the corner because it's below your. If you move the PowerPoint window a little bit up, you can see it. That's another one. Yeah, exactly. But up and there you can see it now. And switch.
All right, good. So actually you've seen the context of the discussion already. We are in the middle of Horizon Europe calls. My name is Rolf Riemenschneider. I work in the IoT unit as a head of sector. I'm coordinating the research and innovation activities under Horizon Europe. So actually, as you've heard, we are in the middle of or the starting phase of Horizon Europe. We already launched one call, and we are about to launch in 23rd of November the second call. So the focus of the calls are research and innovation. So we look a bit forward-looking, and if you talk about IoT, you see there's a bit of a change in the topology of connected objects and devices and systems. So today, many of the IoT deployments and the use cases rely on cloud and cloud gateways. Much of the data is transported towards the cloud and processed in the cloud where you get an app. There's no universal language, quite fragmented, quite complex and expensive for people to use IoT systems or sensors and to deploy it. So actually, for the future, we expect that we see a consolidation. We see much more decentralized processing, as mentioned, keeping data local, but also having more local meshed technologies and decentralized, distributed networking and connectivity. So we're moving from sort of a central topology towards a more meshed topology. What are the technology drivers for that one now? I think at the foremost, it's analytics and performance. I think we have more and more processing capacity of next generation microelectronics. We have more energy efficient chips for central processing, for graphics processing, even for tensor type of chips integrated and embedded in objects and systems. Also, at the same time, we see more lightweight operating systems, also deployed at resource-constrained environments like the edge and more integration. So this is one of the key drivers is computing, is computation, which is more distributed. Secondly, you heard it this morning, it's security and privacy. So if you keep data local, you reduce the attack surface. It's maybe easier to have control over your data and manage your data locally. Thirdly, is decreasing hardware and sensor costs, more integration capacities, more complex system integrations, new functionalities into systems, combining sensing, control, and processing, and reducing the complexity of distributed installations. We will have a speaker also later on in the afternoon from Apple's on smart system integration. You will see more of that. Also, the energy footprint, if you keep data local, if you avoid the overhead and saturating transport networks and avoid central processing in data centers, building more data centers, you might have the advantage to reducing the energy footprint, being more energy efficient, and having a more decentralized energy footprint as well. Open architecture is a key asset. The complexity of the value chain, as well as cost-cutting, cross-domain applications would require that you use architectures which are not built monolithically by one vendor, but are shared across different vendors, avoiding vendor lock-in, and regain market shares in the data economy. Also, next one is the network evolution. I mentioned the mesh technologies, but also take into consideration advances of 5G, campus networks, or 6G. Last but not least is latency. If keeping the data local, you're avoiding latency of our networks. You could do real-time decision-making and automation and control. So to visualize what we mean by that, I think one example is from the healthy living and the smart living area. As said, we expect that more and more sensors will be integrated per unit, per devices. Smartphone is a good example for that will be installed into your environment. And then you have much more data, much more sensitive data, where you have an advantage to keep that local, to keep it around you, to keep control, to have trust into it, and to only get an intervention or ask for intervention with central storage, with clouds, with remote services like remote medicine or medical services, if there's an urgency for doing that or if a real need. Give you a second example from the energy domain, with more and more integration of renewables into the energy grid, with more and more distributed, more intelligent and energy consuming devices. One example is the electric vehicles. You will see this more and more mesh topology of energy consumption, of energy generation, of exchanging energy, and which makes the control of the energy system much more complex. So again, also we talk about, from the application point of view, we talk about an energy data mesh, which is a major demand and a major bottleneck as well for the transition, the energy transition, to move towards decarbonization, decentralization, and the democratization of the future energy systems. The third example, and I'll try to be brief on that one, is from the automotive. The next generation of vehicles is more connected. It's again, it's a good example of more integration of sensors, more integration of radar systems, vision systems, more processing also locally. And then you have sort of this moving, a multi-sensor device or object moving around the environment, where you need information from the environment for autonomous operations, where you need information for mobility services, either for parking or for avoiding traffic jams, or coordinating across different vehicles on the next, who gets access to the next charging station, how to plan your journey, and how to mitigate any constraints or any problems on the roadway. So here, edge intelligence will build on the vehicle as a sensor, but requires this more exchange of information, because you need local information. Doesn't matter, if we have information from the other side of the world, and you need this swarm type of cloud information, interaction with intelligent roadside units, to have smart logistics, smart traveling, and integration also of telematics. So also here we have some new smart products. You have seen that picture already. I think it's the overarching picture of the topology from devices to the edge to the clouds, building a new types of connectivity, including 5G. I don't go into further details, and although this picture has been shown already, I think it's a zoom into our new strategy for Horizon Europe from cloud to edge to IoT under cluster 4. And it was mentioned that we have different pillars, which you see over here. The open source pillar is discussed in the parallel session, as well as the cognitive cloud pillar. The pillar on meta operating system was called for in 2021. So what is open now is decentralized intelligence at the edge, and for that one, building the right development environments, programming environments, and tools for this new topic. And actually, that is the topic of today, why we're inviting you to brainstorming on that one. It's an open brainstorming. It's not focused on limited only on this open topic, which is programming tools for decentralized intelligence and swarms, but we're also looking beyond that. So if identifying gaps, if you're identifying trends which are not yet there, we could still then plan that for the follow-up of the work program 2023-2024. So keep an open mind. The outset of the discussion is about agile and secure architectures for collaborative smart nodes, programming environments, how to make it happen for these smart edge connected nodes, including distributed computing, swarm intelligence, and how to cope with these dynamic groups of nodes across device, edge, and cloud continuum. Thirdly, dynamic open environments. How could you keep with the heterogeneity? What are emerging or possible SDKs which stimulate open architectures and interfaces? How to deal and how to manage the interoperability across different vendors. And the final goal for that one is a reinforced Europe's position in the market of next generation of smart systems. I think that's the overriding objective. And with that one, I close. That is my introductory talk, because I don't want to spend more of your time, and I will immediately dive into the first session, what we call research and technology session, where we have the first speaker to be announced. So thank you very much for your attention, and we go back to Raina. Are there any questions? Yeah, are there any questions from your side, from the audience? Burning one?
There are no questions at the moment, I think.
Okay, there are no questions. That's very good.
So could you quickly stop sharing that, please?
Talk. So let's talk. The first we will start then the session on research perspectives and technology perspectives with a video. Professor Sharam Dusta, he's full professor of computer science and of technology, Technical University of Vienna. He can't make it today, but he has sent a video, and I would invite you then to watch the video and to start the session then with a video.
Sharing, please. Rolf, can you hear me?
Yeah.
Can you please stop sharing the screen? Otherwise, I cannot.
That was.
Thank you. Okay, 1 second.
In this presentation, I'm discussing edge intelligence, which is a new fabric of the distributed compute continuum. And I talk about the research challenges in this field as I see them. Well, I think that we are living in a smart evolution where basically people, software services, and things are being put together by creating elastic systems and elastic processes. And there are many examples for that in smart homes and smart buildings, in e-health networks, in governmental networks, in transportation networks, and in energy networks, where these three components are being put together. People are no longer outside the system, they are inside the system, interacting with the other software services, and the things in the sense of Internet of Things are equally part of that. And it's the first time in history, really, that we have these three building blocks as components being put together in systems. So the question for us is, how do we design, how do we monitor, how do we govern, which are composed out of these three building blocks? And in this presentation, I will discuss some of the main fundamental research challenges as I see them evolve over time. Well, everything is connected with each other. And this is a very trivial understanding. However, it is quite deep if we look further into the world of the systems of today. What I would like to draw your attention to is what I call dynamic compute continuum infrastructures. So typically today we have our systems being structured in horizontal or in vertical domains. This means that we have different building blocks for example, understanding and analyzing energy consumption or air quality or waste of environments or healthcare, etc. However, the current situation shows us very clearly that what we have to do is we have to be able to actually put together horizontal and vertical domains as we go into the world of the systems. So that, for example, we can actually understand the well-being of a certain region, of the people, and combine it with simulation and with mobility patterns at the same time. This is only possible if we actually transcend the horizontal and vertical boundaries of the systems that we have in place today. So the observation for today is basically that there are new families of applications that require real-time location-based access to data from the environment at different levels of fidelity. And second, that we have to include approximate compute and storage resources in closer proximity to data producers and consumers. And this paradigm basically is fundamental to understand. This brings us to the compute continuum as we see it. So the compute continuum basically is an infrastructure perspective, looking at it from the IoT via the edge, via the fog to the cloud. So we no longer see the cloud as the center of our universe of the world of systems, but we see the infrastructure as a whole. We look at it from on the left-hand side, you can see the low reliable, highly volatile and mobile IoT world with a small form factor, battery constraints, etc., being provided and controlled by the users. As we move to the right-hand side, the edge infrastructure with low latency to end devices, closer proximity to 4G or 5G base stations, maybe telco to the right, fog infrastructure typically operated by telcos, and to the right, the usual unlimited compute and storage resources on the cloud. Now, the new systems of the future have to be deployed on this cloud, edge, fog, IoT continuum. We call it the compute continuum. So everything is connected with each other. And the question is, of course, how do we structure the systems? Do I have to decide as an engineer where the system should be deployed in the first place? Everything goes on the cloud as it is today, or some parts are on the edge, some parts on the fog, some parts on the cloud, and which parts are they anyway? So what is the decision making in order to go there? And I think this is the fundamental issue in research challenges. Horizontally and vertically, as this is the whole continuum is structured. So the question becomes, on a research front, which characteristics of such systems should be abstracted as first-class citizens into the underpinning model? And I think that this is basically driving research for the next years to come. One hypothesis is to look into proximity, into context, energy consumption, and such. I would like to draw your attention to two fundamental aspects, what I call elastic diffusion. What is this? Elasticity brings resilience. We know elasticity from physics. It's a property of returning to an initial form or a state following some deformation. So you put some stress on a material, it stretches. If you take that away, it goes back to its initial form. So in the world of computing, you might say, isn't that the same as scalability? Well, in fact, it has been seen similar to scalability. However, I would like to propose a different semantics of how we could see elasticity, where elasticity could be much more than scalability, namely operating in a three-dimensional space. Elasticity is then, therefore, a trade-off between resource elasticity, and these resources can be hardware and software and even people, adding or removing. Second dimension would be quality elasticity of the data input, the data output, performance, quality of data, etc., and the cost elasticity. So we are operating in an elasticity space. The systems that we are designing now, operating in this in this compute continuum, are basically being designed as such that they are aware of resources, quality, and costs at the same time. And this is a fundamentally novel challenge that we have to face, which is going well beyond scalability. So the elasticity model for the future, basically operating on the compute continuum, basically takes into consideration these three-dimensional natures of the systems world that being deployed on the continuum. Namely, the elasticity space represented by these orange boundaries, where we can have an elasticity space function determining the service behavior across time. And secondly, the pathway functions, looking at a particular view, for example, the cost view or the quality view over time, how my application is behaving on that continuum service infrastructure. Now, the second aspect I would like to draw your attention to is the aspect of diffusion. Here I will use a metaphor from chemistry. We call it osmotic computing. In chemistry, osmosis represents the seamless diffusion of molecules from a higher to a lower concentration solution. Similarly, what we aim for is the dynamic management of services across this continuum. So basically that the infrastructure decides intelligently where these services should be deployed, on the cloud, on the fog, on the edge, across the whole continuum, depending on the requirement as we go along. And that is, of course, changing all the time. So the research is basically dealing with the question, where should things be deployed, who is responsible, etc. So this metaphor helps us to understand that diffusion aspect is extremely important. So that's why I would like to draw your attention to these two principles. Elasticity on the one hand side, operating on this three-dimensional space at the same time. The diffusion aspect, looking at it from a behavior perspective, where should things be deployed? We have created a research roadmap looking at this question of edge intelligence and define that from a quality of experience, from an end user perspective. And I give you the reference here because I don't want to spend too much time discussing this. So here we look into 5 criteria: performance, cost, privacy, security, efficiency, and reliability. And out of these end user experiences, we basically determine AI for the edge, looking at topology, content, and service, having its own grand challenges for research, AI for the edge, where we talk about how to establish a model, how to restrain the optimization model, how to work on the algorithm development, so the selection of which edge service devices should actually be responsible for the deployment and execution, and the trade-off between optimality and efficiency. So we should also consider resource-constrained devices. On the other hand, we have AI on the edge, where we discuss data availability, so where we have a challenge of a lack of availability and usability of training data, and the problem of bias of raw data from various end user mobile devices. Secondly, the question of model selection. So the state of the art requires the selection of a need to be trained AI model, and that has challenges in the compute continuum perspective. Thirdly, the coordination mechanism, where we have the coordination between heterogeneous edge devices, the cloud, and all these middlewares and APIs in between. So with this, I want to thank you very much for your attention, and I'm looking forward to the discussion, and you are welcome to reach out via email to me as well. Thanks very much.
This was the video. Rolf, do you want to take the floor back?
Can you hear me? fully?
Yeah, now you're.
So I think it was an inspiring talk about new semantics, how to describe this dynamic continuum between the cloud and the fog and the edge and the IoT. Talking about elastic systems, I think diffusion strategies, where to process the data, I think. And then in the future, we have this more challenging, how to integrate and use that terms for implementing, integrating AI for the edge or at the edge. So aspiring talk, maybe that gives us a chance to start with the first Slido before we move to the next speaker. And the Slido will be around sort of about the audience. What interest does the audience have
to engage in urban
activities? Verena, could you launch the Slido?
Yes, give me a second. First of all, for all of you, I'm posting a link in the chat. I kindly ask you to click on it, and then we will launch the Slido immediately. Or you mean question A, what interest do you have in, right?
Yes.
Okay. So if you are there, I think you should be able to see it now. So please go to the link I just sent you. And I see the voting is ongoing.
Okay, so maybe we can look at the results of the Slido then after the next speaker, but maybe then that you also then announce the next question. What are the game changers enabling technologies supporting a new paradigm towards edge computing? So think about the game changers. The Slido will come soon. But when you're doing that, I will introduce our next distinguished speaker. It's Marc Duranton, with whom we work quite a while now on different topics. He's a member of the Digital Systems and Integrated Circuits division of the Research and Technology Department of CUA in France. He works on the realization of deep learning, edge to cloud, and cyber physical systems. He previously worked in Philips, now in research, and he's particularly involved in the definition of the SRA of the embedded control systems, of the ETP for HPC, and in charge of the roadmap activities of the high-peak network of excellence. I am very pleased to have you here, Marc, and I give you the floor for the next 10 minutes.
So thank you very much for the introduction. So do you see my screen?
Yes, it's coming.
Okay, so thank you very much. So my presentation will be also to make a link between the talk of today, which is decentralizing intelligence and swarm computing, with the hype, what we heard today about the metaverse, the omniverse, and all these various verse. And we will see that even if it's different wording, it's basically the same thing. And first, I would like to go to the context. And here, I'm really grateful that you put the previous presentation before, because we share exactly the same view of the system. So what we have now is that we have the physical world with all sectors of economy that are basically generating data and on IoT or edge device, and that takes decision. The problem that we have here is that now it's a lot of silos. So we need to have a technology which is interoperable, because also from the economical domain, the added value is in crossing the data and the information for various application domain. So the idea is that the edge domain, the edge computing part, basically are the interface between the physical world and the cyber world. So they basically get data from the physical world, process them, and send data to the cloud or to the swarm, and they get action. So typically, this should be done, of course, through secure exchange. But the key point here is that everything should be seen as a service. So typically, when you write an application, in fact, it's composed of various services that could be localized everywhere on the cloud. It could be on the local servers, on the nearby devices, like in the swarm, but it could be also in the cloud. And the key question here is that we need to manage all this dynamicity, so to be able to create new service, to create dynamically new connection, and according to a certain set of requirement. I think the key point now is really this dynamicity of these distributed services. And also what is important to really deal with the requirement of the physical world is that this need to take into account, let's say, the cyber-physical system requirement, like time, latency, locality, energy, privacy, also cost of the service. So the point here is that when you build an application, you need to select the service which is the most appropriate to your current functionality. And typically, we should use service and resources where they are the most efficient. I take a very big example, a very simple example. If you have to get the average of 1 million data, the current model is that the IoT device sends 1 million data to the cloud or to the edge. If the function is only to make the average, it's perhaps better to move the service, so the average, to the edge device so that it could do it locally. So it's not only moving data, but also moving services. And this is also a lot of dynamicity and need to be orchestrated very efficiently. And one key point is that this should use existing technology. This should be built on top of existing technology, otherwise it will not be accepted and it will take a lot of time. So clearly, to make this selection, we need what we call a meta-level OS. So for us, OS is more an orchestrating system that could really select which is the best service according to the current requirement and the current need. Of course, this should run on a trusted a platform, and it should be sure that a company or private data could remain safe. And of course, they are safer generally if they are near the source or near the owner of the data. So really, that means that we need to have a lot of services that should run on edge hardware if it's more efficient. So we see all these edge points that are basically orchestrated into a swarm of services. And here, what we could also see is that we could separate this swarm into two parts. Let's say one are indeed the services, the distributed services that are needed to make a function. But we could also have one other part, which is typically modeling one part of the physical world. So some kind of a partial digital twin for one particular thing. So here, the idea now is that the cyber world could become this cyberverse, where there are a mirror of some of the physical world. And now what we have as interface between, let's say, the physical world and the distributed services, it's the same interface that could go with these distributed digital twins built with a smaller twins or smaller modelization of the world. So clearly now, what we see as the equation of the metaverse, or what the big hyperscaler are now pushing. So of course, the metaverse in the sense of Facebook is only on the cyberspace. The omniverse, so what NVIDIA is pushing, is more toward what we just speak, the interface with the real world to be able to have a better efficiency of the real world, like how to optimize a factory and things like that. So what we could really see as the equation for the future is IoT, cloud, artificial intelligence. So of course, we could regroup this as intelligence IoT or IIoT or intelligent cloud, plus the cyber-physical requirements, which are all this non-functional modeling, like timing, energy, cost, and things like that, plus the simulation of the physical world, the digital twin. So this is what we think is the definition of the metaverse, and exactly the point is that we were pushing in IPIC this idea for a few years, not with the same word, but the key point here and the message is that we should be fast, because this model and the European ethics need to be promoted into this equation, because typically what we see what Microsoft is doing is exactly the same. What they call the metaverse is the link of the intelligent cloud on intelligence edge, working in harmony together with their foundation as a digital twin. And the digital twin are brought to life and synchronized with the physical world using two-way IoT connection. And it's really this binding of the physical and digital that are creating what Microsoft call the metaverse. In IPIC, which was more cyber-physical oriented, we have a different wording for this. So what our vision was, the next cyber-physical system should be cognitive, so using artificial intelligence, but broader than this, with this intelligent connection of devices, choice of the best services, and also predictive. So it's a link to the digital twin, and to make the system to become proactive, be able to react before the event happened, to be more responsive also. And it's not only physical system. What we see now is a system of system that is basically the transcontinuum from IoT to cloud, which is also pushed with the transcontinuum initiatives, the TCI, that is now a regrouping 7 organizations. So this is basically the swarm. So typically, it's what in IPIC we call the CPS square. And really, it's metaverse, the CPS square, on all those other ideas, also what was presented in the previous presentation, is the same underlying idea with different wording. So now, what are the challenges and what could be some potential solution? So clearly the challenge is interoperability and composability, what we could summarize as orchestration. As you could say, we have a lot of these services, and they all need to be aggregated like the piece of the puzzle to get the complete picture. So really the key point is to go towards standard open platform, so to overcome the fragmentation of the current system, and even of the proprietary system that we see really emerging now. All these devices, all these services will be heterogeneous. So interoperability is key. Plus, we need to add this non-functional requirement like latency, cost, energy, and things like that, privacy, so that we could select what is the best service to do the functionality. Scalability, because we see that now an application is ranging from part of the application running on your smartphone or your IoT system to the cloud. And it could finally involve a large number of microservices to make this global functionality. The key point also is dynamicity. All this will be really moving, and it's really like this osmotic computing that was described previously. And of course, with all the key element of keeping the privacy, both for professional and private data and security. So that is really our vision for the next web, which is decentralized, based on shared resources, on linking the cyber and the physical worlds. And indeed, this will be really complex. So that's why we need this smart orchestrator that is able to select how to dynamically link together all the services so that the complete requirement will be fulfilled. So now, what are the key elements and practically how we could do it? So clearly, we see two things. So we will have the basic services that are the libraries function that need to be very efficient, correct by construction, using formal proof is possible. And then how you orchestrate, how you compose this. So this need to be really easy for the application developer or for the user. And we see the next generation that could be done by linguistic programming. So typically the user gives a specification, which is automatically translated through tools into this dynamic interconnection of things. So this is not science fiction. We see the first link with the codex of OpenAI on the work of Stanford with the Almond and the Genie approach. So the second point is that software integration should be done at the highest possible level of abstraction. This is the only practical way to do this. And one possible means to do it is to use RESTful microservices, because the API is external to the software code base that could be written in whatever and run in whatever platform. So really being technology neutral is very important. We need to have also all these non-functional requirements like time, latency, localization, privacy, quality of service, and things like that. So here we need to have some kind of programmation by contract. So each service should expose their contract, and then the orchestrator should select according to the contract what's if he has to deal or use these services. And also, we see this continuum, edge, fog, and cloud. So also, what is also the idea between this idea is also to go towards more dynamicity. So now, basically, we move data. So now we see that the next paradigm will be also to move the service. So really to have what was 20 years ago the goal of Java, so that was to write once to run everywhere. And really here the point is to use, for example, microcontrollers and migrate them even to the edge. So that means that some edge devices, if it's according to the requirement, could do some services and could do even the complete application if possible, and depending on the cost, latency, and things like that. So that's the second level of dynamicity. So dynamic interconnection of services, but also migration also of services onto the continuum and not only the data. So the conclusion of this idea is that basically previously we have very simple edge with simple sensor, IoT, and most of the processing was done on the cloud. So now, currently, we are moving to more a cognitive edge where the edge is doing more functionality, pre-processing data, only sending the relevant information to the cloud and things like that. But we see that the next step will be really to have a decentralized approach, like the swarm, where the requirements, let's say, will be at the edge, where with the interface with the physical world, with the user, and there through distributed orchestrator, they could select on the swarm, that could be either physically the neighboring devices or even part of the cloud and things like that, what will be the best option to do the functionality, and also using this digital twin to be able to modelize also what could be the best option as well. So clearly my message is that indeed now we see the merge between IoT and cloud plus artificial intelligence, but also we need to add this digital twin, this CPS requirement, so that this will really be the next web that could be used to interface with the physical world and help our factory or in our home, in our self-driving car, and so on. So thank you very much for your time, and I will finish on this slide. Thank you.
inspiring talks. So we had 2 inspiring talks. I think the last one on talking about the Metaverse, combining IoT, cloud, AI, and CPS towards open platforms and services. I think, again, you have this vision of a very dynamic environment. I think what is a key element which is new is to introduce data services close to the objects. I think we have to be, we have, you know that if you have IoT sensors, you have an app to the sensor which is somewhere in the cloud. So how to materialize on data services close to the objects. The other thing, what I've taken with your talk is the linguistic programming. I think you know somehow you know how to compose these dynamic systems. You talk about contract-based obligations. Previously, Sharam was talking about cost and benefit functions. And what I take away from the 2 talks is if you talk about data services closer to the edge, you also have to think about decomposing the complexity by grouping these different objects or grouping several systems if they have a common task or a common challenge. You may call that swarm, but however you call it, but you need somehow semantics for describing the problem, and you need logistic programming in order to put that in an environment and make that happen, and give some tools to the developers. So that's my personal takeaway. Is there any burning questions from the audience before I move on to the next group of speakers?
Rolf, there's actually a question from Holger. And Holger, if you would like to speak up and tell your questions, please click quickly on raise a hand, and then we invite you to the stage, if that's okay with Rolf.
That's fine with me.
Okay, then Holger did it. We are inviting you on stage. Here you are. Welcome, Holger. Please feel free to unmute and explain a bit what you mean with your question.
Providing sort of the coverage of the horizon here.
Yes.
What I'm missing, and I think what might be interesting to discuss in maybe some future talks, I don't know, is what are the expectation levels that we have? It's nice to argue about big swarms and we can leverage all the information in all these swarm devices and bring that together. But is that what is likely to happen? Isn't it much more likely that we'll see many small swarms which are going to be isolated, which have to be isolated from each other for privacy, data protection, et cetera, and that's going to be kind of limiting to what you can do by distributing intelligence there? Or do we imagine, on the other hand, as an extreme other case, there's going to be one huge swarm incorporating everything? What are the semantics there? How to delineate that? Is that a topic that we should address?
Maybe a quick answer from my side before I give the floor to Mark. I think we should not think about implementing swarms for the sake of having swarms. I think at the end of the day, we need to solve a problem. And I try to depict or to illustrate that the first challenge is for edge computing is that you introduce data analytics and data services closer to the hardware, the devices, which is a bit of a new paradigm. And secondly, you're grouping some of the devices or the services in a way that you're reducing the complexity. So you may call it swarm, but it's not just for the sake of swarm computing to have swarm computing, but you grouping, should also reduce the data complexity, the task, and also lead to more reactive systems. But maybe Mark, you can complement me.
I think that we should not mix let's say the virtual view or the decomposition of tasks to their physical implementation. For example, we see the move now to, in the automotive industry, instead of having 100 of ECU, to go towards more one centralized function, one centralized computing unit. But this unit will do all the services that are done in the ECU. So now we will still have from let's say a virtual point of view, the same tasks, the same services that are interconnected, but they are mapped here into one single device. So a physical device So the key point here is that is this folding of the several services to where it's more usable. The key point is that we need to have this interoperability to be able to do this. So what we could have is indeed to have local set of services. So for me, the swarm is a set of microservices interconnected. Physically, it could be one swarm running into a single server, let's say. So for me, in my view, I differentiate the virtual view, the composition of the services on their physical localization. I don't know if this answered to your question, but
maybe we are at the start of the discussion. The other part of the question is, how is that can be realized in the real world? Is it not just, a vision or a theory? And for that, that brings me to the next group of speakers, where they're already running a business, so coming a bit more from in the industrial side, but still from the technology side. And I'm very pleased to have Fabrizio Del Maffio here as the CEO of Accelera AI, a deep tech company who is developing an efficient and high-performant, competitive and user-friendly hardware and software platform using AI. So how that will happen, how far are we from real applications, and what are the constraints in real worlds? Maybe we learn something about that one, and how does it link to edge computing? I think that it would be our main interest. Fabrizio, we're happy to have you here, and the talk is you.
Thank you. Welcome to everybody, and thank you for having me here. Well, I will make some consideration about the hardware and the neural network itself for AI at the edge and the end nodes. We all know about that the artificial intelligence is spreading all around us, not only in the industrial market or factory, but in robotics, in retails, which is going to be very big, in smart city. But the main problem is when you go to the edge, you have a lot of constraints, especially from the hardware point of view. You have a limited power budget in many applications, especially when you go to the end node, to camera, to sensor. You have limited computational power, of course, because of this power constraint, but also scalability. While in cloud computing, you can access to more and more power based on your needs, then it's easy to allocate power based on the needs of the user. When you go to the edge, it's very, very difficult to do it. You have also limited connectivity because we are talking about 5G, 6G, but still there are areas that are not covered. And you have also a very high cost performance ratio because the cost of the edge device it's pretty high compared to the performance you have. And another important constraint is also the environment. At the edge, you quite often need extended temperature range, fanless operation. You work in harsh environments. And even this constraint is impacting the selection of the hardware themselves. Well, the problem is AI is spreading, but is also growing. And the algorithms are growing very, very fast. Then if you look at image processing models, they're doubling each after a year. But if you go to language processing models, like a GPT-3, that is one of the most advanced nowadays algorithm, they are actually increasing 20x year after year. Then it's clearly that this trend is not sustainable. You have algorithm growing very fast, and you want to decentralize intelligence going to the edge node where you have less power, processing power, and a lot of constraint. Well, how to solve this? First, we have to look inside the neural network themselves. When you go to neural network, you notice that neural network, they are very large metrics where you multiply the data, and then 70% of this operation are a multiplication accumulation. And this operation, they are not well mapped into the architecture. Then while in the cloud, you can still have access to heterogeneous computing. When you go to the edge, you have a lot of constraints. Typically, you have one processing unit, and this processing unit is very generic, and then almost never optimized for this calculation. Another important things to look at is that today computing is not designed for processing large amount of data. Then you have still the processing unit and the memory, and you have a very large data exchange, especially when you go to neural network and artificial intelligence. And the problem is that this data movement is the main source of power consumption. Then essentially the architecture of processing and memory completely separated doesn't fit well the requirement of artificial intelligence. And again, while in the cloud you can access the heterogeneous computing, in the edge you don't have this. You don't have this ad hoc computing. Well, there are some trends and tricks we can play, and one of the important trends that you have is that neural network are going to you can quantize the neural network, then you reduce the precision, and then you can lower the power consumption, increase the efficiency. Essentially, doing so, you can take the neural network that are run in the cloud and then change the precision and run them in a more efficient way at the edge. But there are some costs for this. One is the accuracy, which is reduced. Second of all, at the edge, you have fragmentation of hardware, and this process of quantization is typically it must be customized based on the hardware that you are going to use. Then you cannot use the same quantization for any hardware. And also, it's not really trivial to do this process for any hardware available. Another important trend is the compression and optimization. Then you take a network and you try to optimize to reduce it, to approximate the network, then to make it lighter and make it run more efficiently at the edge. But again, this process has a cost, is lower accuracy, and there are no proprietary tools. And this is an extremely important problem that we have to solve. We have to address having an open source tool to do this compression optimization, and a common tool for everybody. And luckily, there are some foundation open foundation that are addressing this. And for all the people that are interested to have a deep look at this, I suggest to have a look at the TinyML, which is a foundation which is addressing exactly this. Try to take a large algorithm and help to port this algorithm to devices which have power constraint and also computational constraints. But in general, even if you play these tricks, you have still limitation. And then it's really necessary at the edge to address the problem on the hardware. Then try to redesign the hardware, to reinvent the hardware. And I think one of the most important architecture that may deliver benefit at the edge is this called in-memory computing. Essentially, it's a way that allows to process data within the memory. You take the memory, the SRAM or whatever other kind of memory, and you modify this memory to process the data. It means that the data doesn't go back and forward from the memory to the CPU, but is processed inside the memory. This allows to have a very extremely high throughput, high efficiency, low power consumption. You can reduce the footprint of the circuit, and it's possible to have it in digital and analog domain. Most of the data and the sensor out there are analog. Then in the future, you will see more and more devices using in-memory computing and analog in-memory computing to save power and to increase then the efficiency and the throughput for operation at the edge. Of course, there are costs to do so. Precision is reduced when you do in-memory computing. And also, it's non-trivial to map the network and quantize this network. And another architecture, which is going to have a very large impact, probably in coming 10 years, so we have to wait 5 to 10 years to have it really on volume, is the spiking neural network computing, which is mimicking our biological brain, where information is time-coded. Then it's a different way to process information. But spiking computing can give extremely high efficiency. It's possible in digital analog domain. It can be combined with in-memory computing then to increase further the efficiency, and then to process the data directly in the end node, to have always on end node architecture, and then to have a distributed intelligence. Of course, there are, even in this case, a limitation. The hardware availability, hardware is not really there. There are some hardware, but very few solutions in the market, limited tools, and still the scientific community is still more focused on standard computing, which is using the cloud and not at the edge. But we see an important trend, and we see spiking computing and in-memory computing to impact over the next 5 years. And then the takeaway is that AI at the edge and in the nodes needs optimized hardware and neural network, both of the things, if you want to really have a decentralized intelligence. Quantized and optimized neural network can improve efficiency and throughput on standard hardware, then without changing the hardware. But new hardware technologies such as memory computing and spiking computing promise to deliver large advantages. And likely European Union is supporting research activity in this direction. And I look forward to see a large impact of European enterprises in this market segment. Thank you so much.
I think that was a very useful talk about the need to look for new hardware, not only the standard computing capacity what we have, but processing capacity tuned also to new tools and new ways in integrating AI algorithms. I think that is a key message, and we have to bear in mind that with the need of data processing close to the edge nodes, we also need new computing architectures, new ways, new algorithms, in order to benefit from the information and create the knowledge over there. Otherwise, we just create a data deluge at the edge, which will not bring any cost benefit. So moving on from the basic configurations on processing, I'm pleased to invite Purushottam Poswani, also from an application perspective, from Atos. Purushottam is the Chief Technology Officer at Atos and an IoT lead in the Asia Pacific region with more than 20 years of cross-industry experience. And he's very passionate about digital technologies around IoT, cloud, machine learning, blockchain, and AI. So in the center of what is our interest and discussion at the moment, and we're very happy and pleased to have you here, and pass the floor to you, Purushottam.
Yeah, can you hear me? Am I audible? Rob, can you hear me?
Yes.
All right. Okay. All right. Okay. So good morning, everyone. It's a pleasure to be part of this digital autonomy event. Today, I will present the swarm intelligence concepts, architecture, and the vision way we see, and how we have done for a couple of projects implementation when it comes to swarm intelligence. My name is Purushottam Poswani. I work for Atos APAC as CTO. Okay, so we heard very interesting things about swarm computing in the previous presentation. Now let me give examples of swarm behaviors seen in nature. A flock of birds, a school of fish, or colony of bees, and an army of termites. Now, if you see, one of the commonalities in all the examples is self-organization, collaboration, right? Which really helps animals, birds achieve the common goal. Each of them adopts their behavior in the group's interest. Taking this motivation last year, my colleagues and I developed a paper on swarm intelligence and how we can apply those principles not only to technology, to organization and systems. So what I'll be doing in my slides is I would like to summarize the research done. And based on this research, last couple of months, we have done some pilots, some projects, which I would like to share my experience as well. So now, if we see, when it comes to swarm intelligence, there are few key characteristics to make swarm work. On the left, I've highlighted self-healing. The collaboration within the swarm participants works even though the participants in the swarm leaves or the new participants enter the swarm. The second is on the self-configuration. So based on the participants in the swarm, the system can self-configure based on the characteristics each participant possesses. And last is the self-optimization. It is able to scale and optimize based on the operating conditions, environment, or for instance, what Mark mentioned in his presentation as well. Now, based on these characteristics, I would say there are some key principles which each of these participants has to adhere to. First one is proximity, which is a sense of togetherness through network. Leadership, which is facilitating the community. Memory, which is within the swarm, and the individual, and most important is a standard way of information exchange and cooperation clustering. I believe with these key principles, the individual knowledge, when can combine together, will definitely yield the smart results. So moving on, I would say it's not that we don't see this man-made swarms, so we have really kind of taken this animal swarms principles and have applied it to man-made swarms. And definitely we see in autonomous vehicles, for instance, what Ralph mentioned, or automated supply chains. But the question here is, how do we go mainstream? How do we kind of take those concepts and apply for different industries? Okay, and that is where this is a research which we did, and basically based on the couple of customer engagements, what we see is what is a demand. So as my fellow presentation talked about, that current IoT is more of a static architecture. You have typically edge sensors, edge, cloud, and but what we see is eventually more and more devices are coming, more and more sensors are added. So the key important aspect is how do we move from the static structure to dynamic structure. Okay. The second thing which we already talked about was security and privacy. How do we ensure that the data remains within the edge and do not travel to cloud where we have privacy issues or data leakage issues. Third thing is about efficiency and CO2. And most important is it really productive that we send all the information to the cloud, and for which we need to build data centers and have a lot of emissions, right? And last not the least, at least in the cloud environment, we see this concept of decentralized learning. Okay, so eventually this is what is the ask of the industry. Okay, now at the same time, as a part of this research, we also looked at what are the technology advancements which are happening. So edge computing, we already talked about algorithms and data. Again, we talked about with evolution of transfer learning and things like that. This is very important. Third thing which I would like to highlight, and this goes back to the question which was asked, that whether we're going to have one single swarm or we're going to have multiple swarms. And for this, I would say with this decentralized ledger, the evolution, the stability is coming. And for sure, this decentralized ledger probably is a way to share this data or to ensure the traceability and privacy. And last not the least is on communication and operation models. So based on this technology evolution, taking that swarm principles, actually, I believe that we would be in a position to create this highly dynamic on-the-fly systems, which will be powered through the swarm intelligence. Going forward, what I've done here is I've kind of created a scenario, which is a simplistic way, because when we go and present this concept to swarm, it becomes very techie kind of stuff, right? I mean, that is where I put up this case of a remote infrastructure inspection use case. Here, the idea is we're building a swarm of heterogeneous devices. So in this case, in this scenario, we have a drone, we have multiple edge systems, we have traffic signal systems measuring the air quality or the pollutions, for instance. And the concept here is, for instance, in case this drone says, I want to have a situation, and I want you guys, the edge devices, to get this model trained or to tell me what I have to do, So here, for instance, one of the edge device would run out of juice, and then the second edge device would take over. So again, this is the concept of swarm, where the self-heal, the self-configuration plays an important key role. Okay. So taking this forward, what we see is the system is moved from the centralized setup to the decentralized setup, where it's more of an open access, the data resides within the edge, and it's more of a dynamic situation. Now, moving forward with this concept, I would like to highlight one of the use case or one of the project which we did for one of the smart city. The need was that when the pedestrian is walking down the street, we should be in a position to track this pedestrian. Now, if it was in an old way, basically what we will do is we would send all this information to the cloud, and all this processing would be done on the cloud. But here, what was done was we had set up a swarm of cameras and edge devices, and these cameras and edge devices were collaborating, were extracting feature, were sharing the knowledge, and through this swarm, we were able to identify the path which this user takes. Okay, so again, it's a fantastic example of how a swarm of devices can come together and solve a certain issue. Okay, now with this, I would like to share in terms of if I have to do this swarm intelligence, what are the building blocks? What would be my reference architecture? So here I will spend a little bit of time. So from a building blocks perspective, I have highlighted this into 6 on the extreme left-hand side. So first, we would need a lot of algorithms, and these algorithms are available, and these algorithms are being developed with the nature in mind. So that is where we have this algorithm called particle swarm optimization or ant colony optimization, for instance. And what we do here in this algorithms is to search to take an agents, and these agents are able to solve a certain issue. Security, which we already talked about. Decentralized learning. Now, this is the most difficult part, because you are in an environment where the different edge devices or different IoT devices are heterogeneous. So how do you ensure that the models which are built are able to run across those devices? And most importantly, these models have the required accuracy, because the data is still within the edge, and we are this and putting at the central place. Okay. Most important, asset management and monitoring. Now, eventually, the example which I gave about this swarm of cameras and video intelligence, the issue is once you have this project and implementation, how do you manage it? How do you manage the edge devices? How do you manage the firmware updates to these edge devices? How do you manage this edge, for instance, going off and on? So most important is asset management and monitoring, and of course communication schemes, which we already talked about. Now, based on this building blocks, what we did was within our architect team is we kind of created a blueprint of how this architecture would look like, and that is where I will spend a couple of minutes here. So basically, the way we have set this up is into different layers, and I would focus now only on the edge layer because the cloud layer is quite familiar to a lot of people. So in the case of edge layer, it is structured into 3 different layers. Level 0, which represents the IoT device and sensors that are the main data sources, but are also enabled with rapid actuation capacities. Level 1 is about offering the connectivity services that permit extreme low latency. And level 2 is about enabling elastic computing and storage capacity at the edge, as well as access to the traditional cloud computing capacities. Now, I would, of course, we don't have so much time, but I would like to take some of the concepts which, for instance, Mark also covered. So few components which are important here is the swarm instrumentation. Now, this instrumentation basically enables the level 0 devices and the edge computing to participate in a Swarm service network, where it will publish its resources and status, right? Now, since we know which resource is busy with what and its status, that is where the Swarm orchestration comes into the picture. The Swarm orchestration basically takes the decentralized management framework, and what it does is it bases its decisions on the collaborative attributes and an entity's object lifecycle properties, like its location, like its relation, its asset condition, and most importantly, its contextual and environmental lifecycle properties. Okay. Now, going further deep with this reference architecture, I thought I should also share in terms of what are the SDKs which are available, what are the components which are available in an open source world. Okay. So, sorry. Okay. So this is
I think we have to come to an end.
Yeah. Right. So this is my last slide, Rolf. So this is what the tools and the framework which we have used and which we have placed. So the message is that it's no one size fit all. It's an evolving ecosystem, and it really helps to orchestrate across all these levels, basically. Yeah, and then this is the last slide in terms of from the vision and challenges perspective. I would not cover, but one of the key aspects here would be on Swarm teams, and the Swarm teams basically replicate the Swarm in the digital world for simulation, orchestration, and Swarm instantiation. So with that, I would say more details are published on the various journey documents or in the white papers, which I put it on the screen here. So if you would be interested, just visit this PDF documents. It gives more details. Okay, and that's all. Thank you very much.
Thank you so much for giving us the insight in that and your approach. I think you've taken up many of the ideas before we had beforehand. Talking about collective intelligence, you need the local interaction, the self-prioritization of tasks of a group of objects or systems, and also, have a clear based on interaction based on contracts. Your approach and having a reference architecture with building blocks and to sort of start designing blueprints of implementation, I think makes sense. I think, gives you closer to mainstream the technology and to make it happen, because I think, if you have all the nice ideas and the vision, and then you need very quick concrete steps, what could you done in the real world and what are applications, and particularly the famous intelligent roadside units or the intelligent crossing shows the demand of have a very flexible configuration and accelerating the interaction between objects once there's a critical interaction, and then deciding also who takes actions and informs the drivers and the pedestrians. Thanks so much for the inspiring talk, and we move to the third speaker and the last one of this panel. It's Jaka Delsing. Jaka is professor at the Luleå University in Industrial Electronics, and he chairs the cyber-physical systems activities. He deals with research related to Internet of Things, systems automation, particular focus on applications in automation to large complex industrial systems and societal systems. He is also active and a member of Insight, formerly known from the Artemis IA, linking to embedded and control systems, and he's board member of Process IT, a Swedish process network in innovations. Jaka, the floor is yours.
See the swap card window. We saw your presentation before. Can you unmute yourself? Jaka, you're still muted. There is on the down at the end of the window, you can see, I can see that you can see, yes, perfect. Yeah. The button was good. Okay, yes, now we can see the screen again. It was better before. I can. Yes, perfect, but I cannot hear you, Jaka. Please unmute. I cannot unmute you. You need to do it. It's at the end of the window. You cannot do it. Did you enable your audio settings? Hover over the screen, please, with your mouse now, and there you see it. Down, there's the red button, and the very left one is the unmute button. Yes, click it. And you need to enable permissions of your browser. You should have received a pop-up for that. We tested it in the rehearsal. There it worked. Jaka, otherwise, Rolf, shall we move on otherwise? And Jaka joins again and maybe with a different browser, the one you used in the rehearsal?
We heard about divisions, we heard about the key technologies, particularly also about road and reference architecture and building blocks. Maybe we ask the audience, you know, in their mind what they heard is what do they think are major breakthrough technologies for the next generation IoT and edge computing. And we asked the Slido for that one and to give you some feedback, some linked to what was said already, but some, you know, are much more maybe oriented to other sites and to have the view of the audience. And while Jaka is, I think he's almost ready.
Yeah, well, we see your presentation very nicely now, but Jaka, I cannot hear you. You need to be able to hover over the screen. And then you should see the buttons. And then there's the left one where you can click on. No? I don't know. I cannot unfortunately do it for you. So maybe you leave this meeting, come again and enable the audio settings, please. And Rolf, you just mute on. I muted you, Rolf. You need to unmute again. Sorry for that.
Yes, otherwise I would propose, it's quite unfortunate if Jaka cannot join, but maybe he can join in between and we start the panel discussion.
I think he's unmuted now. Jaka, say something?
Can you hear me now?
Yes, there you
yes,
are.
Yes, we can. Now, I think now we go back to your presentation.
Very good. Then I'll share my screen. You see my screen?
Excellent. Go ahead.
Very good. Sorry for all the hassle. I'm going to talk about industrial plants, and they actually are systems of cyber physical systems. And a couple of minutes ago, I came from a discussion with a mining company, so that's why I have a mining picture here of a plant. And it's quite interesting to see that they draw all these type of plants with just the material flow. And this is how people think. And they know there is an information flow as well. But that's never drawn by the people who are actually designing these type of machinery, not to begin with. So it's kind of an overlay on what we see as the kind of primary thing of actually producing, in this case, copper or cars or shavers or whatever we think. But the information part is a much more integrated thing, but it's not kind of designed and worked that way with the existing automation architectures and implementation we find out there in industry. So what are we looking at? We are looking at the production plant, which is a system of cyber physical systems similar to what Mark talked about before, but it's an integrated material and information flow situation. And what we're looking forward to is flexibility of this production plant that has been talked about, for example, in the Factory of the Future and EFRA for a number of years now. But this is not only to assure that there is flexibility on the material flow, but it's as much a flexibility on the information flow and the automation part. But the current technology we have does not give us a flexible automation. Moving, for example, a nut runner 15 meters from one workstation to another at the Volvo trucks is an operations of 100k euros in 6 months. Sounds ridiculous, but that's the reality currently. So these are the things that the industry is facing right now. And where are we then to work with this? We are looking for automation flexibility, runtime reorganization, engineering simplicity, these kind of things. But which are the technologies that's currently being looked at, and how do we kind of proceed in moving there? We've heard about microservices, service-oriented architecture, but very much that these should be at the edge, and that we need interoperability. And here, autonomous translation between the involved microservices is becoming a very important part to actually reduce cost. But also there's edge virtualization, that we should be able to reorganize things over time, not primarily being executed on the thing that we started with. So kind of disconnecting hardware and software to a way where we can reorganize things and make that fast, meaning we can support runtime evolution. And for this purpose, we also then need, we project open source implementation platforms, which will enable us to do these things. So what's the kind of problem we then start to face is that when we see that we can integrate all these kind of things, but they should create a functionality. But at the same time, they have another dimension, which is security. We need to protect ourselves from any evil things that can harm the functionality. But the functionality can also create harm to machinery, to people. So safety is another dimension. Then we need to earn money on this. So business models connected to all this functionality, where we integrate value networks, becomes a very integrated part of this type of very complex system of cyber physical systems. And another part here is machine-to-machine transactions, since administration today is costly, and low cost or automated administration of business becomes another part which we need to have as another dimension in this. Maintenance, of course, which has been mentioned, and there is a number of more of these. From what can we learn to actually bring all these things together? Since all these dimensions, they are non-orthogonal, they are time dependent, and these kind of things are changing with different time scales, and it's super complex. The only thing that I know about that actually has get this going is biology. If we look at our nature, we can see that everything from bacteria, plants, animals, humans, and all this kind. We're actually living reasonably well together. Things happen now and then, yes, but on a large scale, things are working pretty well. So it's interesting. We probably need to look at biology to actually understand and get a better understanding of how we can actually get these things to work together. And at least as far as I understand, we are quite far away from actually being able to optimize these things in a practical way, and where this can be done to reasonably low cost. Which environment are we living in? We are living in and OT, operational technology from legacy things using classical production architectures like ISO 95, which has a very stiff implementation from the automation viewpoint. And we are then moving to an even more complex situation, but using newer technology with the Industry 4.0, Raumi 4.0, and internet technologies. These things have to live together for a long time. And this is where interoperability then becomes super important. And we've been moving on this direction for quite some time. And there is a number of European projects that has been critical to actually move these things. And here is kind of a timeline and what has been done here. For example, the Arrowhead project was working a lot with IoT, OT interoperability and this translation capabilities. Productive 4.0 created the IoT, OT integration platform, which now goes under the name of Eclipse Arrowhead and is open source. And the current Arrowhead Tools project is looking at efficient solution engineering based on that such platform, the Eclipse Arrowhead here. And here we had a very ambitious objective of reducing the cost of 20 to 50%, and people kind of that we don't believe in that. But it's interesting to see that the actual results right now is already 30 to 95% of cost reduction after 2 years. Just to give you some examples of what is achievable with what kind of was partly projected in some of the other talks is, here's an example from Infineon. Installing new sensors previously took 3 months and involved at least 6 people to actually get it going with their existing architecture, how they work. And with this new approach, and where they started from zero, they didn't understand this when we started. And now after 2 years, they are down to 1 day and involving only 2 people. And this is considerable cost savings in the daily operations of factories. Another example is from the building manufacturing industry, when people going from architectural drawings to robot production. This was 2 years ago, 7 weeks in lead time and a lot of errors. Right now, they are down to 1 week and no errors. And the expectation is that they will be down to 90 seconds in lead time and no errors, which will be April next year. And considerable amount of engineering time saved and by taking some of these approaches that we've heard in some of the existing, the previous talks. A final example is from smart home, smart energy, where we're integrating IoT platforms into the smart home. And the previous approach was based on some IoT platform thinking, proprietary stuff, and now we are bringing this together into a service-oriented, at-the-edge service integration, and a couple of these open source technologies like Kapua, Arrowhead technology, Arrowhead framework, etc. And the expectations here, or not expectations, this is what I see already. They can go from 2 to 3 months, depending on the size of the installation, to days. So a factor of 30, roughly, is the savings in this case. So it's going from heterogeneous monitoring branches to unified monitoring services. And these are concepts that companies now are bringing together. So it's possible to actually take these kind of visions and make them for real. That's kind of what I'm saying. But we still have a long journey to go to actually exploit the full power of this. And that's the integration and what I think Mark was talking about, composability and these kind of things. But this is super important to be in focus for the future work in the European Union. Thanks a lot for the time. you gave me.
Thanks so much, Jacke. I think that brings us basically to the last part of the session, where I invite all speakers to a panel, Mark, Fabrizio, Pushottam, and Jacke. I think we have seen that we have a lot of distinguished vision. We know there's a need more for dynamics and dynamic engineering, but also more self-adaptive tasks and intelligence. You may call it form, you may give a different name. I appreciate that we had a discussion about, how would a reference architecture would look like to sort of illustrate, what are the main means and what are the building blocks. And the last presentation from Jacke was about the industrial side. Particularly here, it's a quite conservative sector, and data services or data technologies as such are quite critical and difficult to implement for these sort of conservative industries. So I2O2 integration is known since a while, but again, how to make it happen? What are the key technologies who would approach or will emerge at the edge, and who are the main stakeholders to invest in these technologies? Because at the end of the day, it's a gateway or it's a hardware where you have to invest in order to put it on site. Before starting the panel and looking at different questions, I would look also, give a look at the outcome of the Slido. Maybe Verena, you can show some of the pictures.
Probably not happen, but in case it happens, and this thing here is just refresh the page. It will not happen, hopefully.
We can't hear you. Or if it's too complicated, then we do it later. So for the panel discussion, I think the first question was, what are the major new paradigms for connected objects and systems? I think we discussed that at length. Maybe we can shorten that one. We know you mentioned the new dynamics. Though to have dynamic service allocation, to have dynamic data services, as well as to trigger an interaction group-wise or swarms, whatever you call it, between the local system, the local objects. What I wanted to ask you here in that context is how to make it happen, how to mainstream that. What are the needs or what are the low-hanging fruits for programming tools, engineering tools, or existing building blocks in that area? Jacke, you started to talk about tools which are available. So what are the main characteristics of the tools? Do they support streaming of data? Do they support deployment of microservices?
Microservices and agree. Yeah, it seems that microservices, service-oriented architecture is the common denominator for most approaches that I have seen. And then it's important to get open, stable platforms, since it's quite clear that single companies cannot provide everything that's necessary. But open, stable platforms where we can actually integrate, handle security, orchestration, registration, etc., across various domains.
And you mentioned some Eclipse tools. Is that sort of available as Eclipse as a framework, or is it just in the main?
No, it's available. Version 4.4 were actually released 2 days ago.
Okay, and Pushottam, you also mentioned that you're working on standard tools and open source components. So what are the main building blocks you have already implemented? Or what are already available to support the new paradigms?
So this is sorry.
Available building blocks are the key things to create a service-oriented architecture. So this lookup, discovery capabilities, late binding, and these kind of things. That's already available. And then there is quite a large set of things for interoperability across various OT technology and IT technology. And then also a number of support systems to address interaction, system-of-system building, and engineering of these. And there are also prototypes for this, like business models and machine-to-machine transactions. So there's quite a big set of technology that's already available. And those things that's released are, certain parts of these are already used by companies in actual business. Things from sensors up to MES system has been implemented and is running in as products with customers based on this technology.
Okay.
So Rolf, in addition, what I would like to add is there are a lot of frameworks which are available in terms of doing orchestration, because when it comes to decentralized setup, as I had presented or as Mark had mentioned, you would need some kind of an orchestrator. So such orchestrator is available. The second thing which I see available again in an open source world is what TensorFlow. So they have now a federated kind of slide. You can actually run TensorFlow federated for doing your time series analytics or you doing an image analytics. So something like this is already available. And then when it comes to a decentralized communication, I would say at this moment of time, in terms of gossip protocol implementation, which helps you to set up, what you talked about, the mesh of devices. Again, this is something which is already available.
Okay, would the others would like to comment or step in? No, I don't see any other comment. Maybe we move to the second question. So what are the game changers enabling technology supporting a new paradigm towards edge computing? We heard from Fabrizio, you need a new computing architecture. So how far are we from industrial uptake or mainstreaming of these architectures?
Thanks for asking. We are not far. First of all, European Union is supporting widely this in-memory computing project, neuromorphic activities. Then this is already as a positive initiative, considering that the business-to-business market is dominated by European SME, and therefore Europe is going to play an important role on this. We are not so far, although there is still there are some pieces of the puzzle that are missing. I think that one is that there is no uniformity in the hardware and the software tool. Then there are a lot of scattering activities, but it's difficult to have common tools to be used. Practically, there are various ways to implement the spiking neural network computing, various ways to implementing memory computing. Each different way needs different tools. And I think that there is no standardization out there. And this is a little bit slowing down the adoption curve. And the other important problem, I think, is always the problem of data that we already named, and the fact that all these new computing paradigms need data to be trained, and we need data, industrial data, and this is a common problem around Europe, that we don't have a data for industrial application where companies can work with, and this is, I think, something that should be addressed.
Yeah, about the time and the scoping, Purushottam, you mentioned the smart roadside unit or the smart crossing. I think there's a lot of advances, particularly in intelligent cameras and image processing. Is that the way to go, the driving applications?
Yeah, that's right. Yeah. So, I mean, if we look at vision kind of technologies, what we are seeing is a lot of cameras are now having this chips available where you can do a lot of analytics on the camera itself. But one of the other aspects, which I mean, when we're talking about the swarm, is this orchestration, right? And we're talking about, how do I take some of the service which is on the cloud and move directly on the edge. So one of the game changer I would also add is this containerization, right? Now this containerization is available on the edge devices. Now eventually that really helps me to do this service federation, right? I mean, I can take some service from cloud and move it to edge or vice versa. So again, that is very important, I would say.
Mark, about the containerization and the service federation, how far are we from implementing your vision then on the swarm and decentralized intelligence? Well, is that the game changer? Is that already available, or do we still need to further tools for that one?
Well, there are first implementation even on embedded system of containerization and on the virtualization. The point is that still the problem is that it's not yet mainstream because of the lack of tool. Also, it's a little bit let's say not in the mainstream thinking of application developer as well. And I think it's the same problem for neuromorphic. People could use it, but they don't know, and so also the training of the new developer into this new technology will also help. But yes, indeed, there are still development required.
So Rolf, it all boils down to the talent, right? If you have the talent or how you train in this new tech stuff, right? From a tool, productivity and things like that, then definitely there is an evolution which would happen for sure. Yeah, that's what the hyperscaler showed us.
Yeah, the main problem is how to make it more mainstream. So we were talking about in memory computing about a neuromorphic. We could hide into one application or into one smart camera, but that's still a specialized team that will develop it. So how to make it more available to other people? So so we were developing tools since 10 years that are interfacing neuromorphic spiking architecture with classical for the learning, being able to make the translation and things like that. But that's still not a mainstream, and people are not yet using it. And it's a little bit also a chicken and egg problem. If people are not used to it, they don't call on not using it. So then the development of the hardware and the software solution will be mainly stay in research and will take time to go to the industry. So how to kickstart this value chain? I think it's important to see how to do it.
Okay. One of the important points here is then training tools and how you can actually tailor these for various players in a value network.
Yeah.
So in my world with production, we have like automation architects, and then you have IT architects, and then you start to have network people. You have people that code these solutions, and all of them have different skills, and we need to talk with them and provide this information tailored for the different competencies that's around to actually achieve the integration that will, like in my case, will impact the capability of automation in a plant.
Okay, I think that goes back to that you need the right skills for the developers in order to manage the complexity and you have to talk to the system integrators, so those who know the processes and the industrial details and the constraints. And how to kickstart it, I think that is one of the chicken egg problems. I think that's why we go for research and innovation actions in the first place, in order to bring the different tools together, to different disciplines together on the one hand, but also to have sort of a proof of concept that we need first demos or proof of concepts in an application context in order to make it happen. I think I think from what I hear from you, the design of our topic is fit for purpose. A question is for you now. Some of you may have read the work program. Do we miss something out, or is it sort of for the time being sufficient, to start with, and or are we going to be too late?
I think we have the brain, we have the idea, but perhaps we lack the coordination between all the activities. So you see in the past, in the IoT domain, there are several projects and developing various API, various platform, various solutions. And of course, that trigger new startups that were making the gateway, the software gateway between different protocols and things like that. But I think that this is the strength of the hyperscalers, so that they have one solution, they impose it to their ecosystem, so they are all going, or in their ecosystem, are going into our direction. In Europe, we are a little bit scattered into a good idea, but going into different directions. So I think that coordinating, having all the team working in a neighboring domain, working together, trying to adapt their solution so that it could be compatible with the other or be an extension of the other, I think it's really what I think is missing. Having more solution, more people, more SME, more startup going into a similar solution or solution that complement to each other. Here we could have the strengths because we don't have in Europe the big hyperscalers like the Google, Apple that are imposing their solution in the domain of IoT. And as I show you in this next web, going from IoT to the cloud, they're already starting to go into this direction. So we need to be fast, and we need to go like a swarm, let's say, coordinating. So we have a lot of independent solutions, but we need to be coordinating to have a global goal. I think that is really what I see is missing. So it's not really the technical, the knowledge, but it's more this idea of going together.
Okay, I think that's
good. I agree with you, Mark, on this. I partly agree with you that we are moving in one way, but we don't have the technology to actually do this integration, the composabilities. How will the system actually work together? We don't have that technology. That's very clear. There is not even theory to handle this. And
I think that's a valid point.
That I'm missing in the work program.
Okay, I think that's a valid point, and definitely we don't have that in this part of the work program, but we have a session in the afternoon where we say, well, if we talk about an edge operating system, if we talk about new technologies for data handling at the edge and handling data locally, that we still need a very strong push from the system integration part, and that could only go with the system developers and the domain specific. So that's why we're proposing for the next work program also a downstream action on domain-specific pilot action in order to focus on the system integration combined with the edge computing and the data management at the edge. And there's one part. To close the panel, I think if you look at the word cloud, which we have from our poll, particularly in our panel discussion, we talked about virtualization, containerization as the main element for orchestrating the different services at the edge and for the service federation. I think that is very well reflected. What we did not touch upon is the networking part, which came a bit short in this discussion. but maybe this is brought up from the application view, and I would to thank very warmly to all the speakers so far, Fabrizio, Mark, Potosharam, and Jerka. And I would move then now to the second panel, which is the application panel. As I understood from that we need a short break, Verena, is that true?
A few seconds, okay? I need to stop the recording and resume. Give me a moment.
Okay, good. Okay, thanks so much. So we had the technology view and we had the research view with a lot of strong position on the vision. We looked a bit on the gaps, and the question was always about mainstreaming, how to make it happen. And we're now looking forward to talk about a bit about applications, particular when Jerka talked about material flows in factories, that relied on some bio-inspired algorithms already in the past. I think that was demonstrated, and maybe we can learn something more from Michael ten Hompel. He is professor in Dortmund, actually managing director of the Fraunhofer Institute of Material Flow and Logistics in Dortmund, and became head of the chair of materials handling and warehousing at the Technical University of Dortmund. So unfortunately, he cannot be here personally, but he sent a video message forward to his key messages. Please, Verena.
Ladies and gentlemen, we live in a time where the digitization of everything and the artificial intelligence in everything will change everything for all of us. And let me say, we are facing a real new world, which is too complex to go for it alone. More and more, the complexity of logistics systems can no longer be mastered with classical algorithms and the classical operations research. This is especially true for complex supply chains and swarms of autonomous guided vehicles, as you could see here on this slide. These are the so-called load runners, and this is a typical representative of autonomous swarms in logistics. Let me say it's the first representative of a real swarm in logistics. And as I said, such a real swarm of autonomous interacting vehicles cannot be controlled with classical algorithms. Also, the use of nature-identical methods is not really suitable, as we thought some years ago. For such a solution, artificial intelligence methods, and especially machine learning, is absolutely essential. But on the other hand, the training of the vehicles in reality would take too much time. It would take days, months, maybe years. And that's why we use the simulation-based learning methods. And this is what you're seeing here. On the left side, the simulation is running, and this is not an animation, this is a real simulation in which neural networks are taught. And then the algorithms and the neural networks are transferred to the vehicles. And on the right-hand side, you see a real swarm where the vehicles are acting as avatars of the simulated reality. And let me say, this is really not a fake. This is really reality. This kind of simulation-based AI is one of the next big things, or is the next big thing, not just for logistics. Now, the next crucial point I'd like to point out of the actual development is the temporal coincidence of several developments and the simultaneous and more super exponential explosion of computing power. From Industry 4.0 and the Internet of Things, including artificial intelligence and AI in edge devices, edge AI, over via real-time capable network and 5G, Wi-Fi 6, you name it, AI-based platform, everything is real, is reality. Blockchain, no business. This becomes more and more reality in distributed ledger systems. Decentralized autonomous organization, not just control, but also the organization of complete supply chains become more and more reality via decentralized autonomous interacting entities. Swarms of autonomous robots, as you saw in swarm of our load runners, virtualization, simulation and virtualization, immersive technologies like augmented reality, virtual reality, which connect the people, the human beings with the artificial intelligence, up to cognitive computing and brain-machine interfaces, which you can see here on the left side, where one of our employees controls the AGV in front of him while it starts, and it's his brain waves. This is also not a fake, but of course this is real basic research, and it will need some years, some decades, I think, to use brain-machine interfaces for industrial use. But this is also not a fake. The man on the picture controls the AGV in front of him via its brainwaves. Now, last point I'd like to make about digitization concerns the immaterialization and digitization of the complete economy. We are moving from an internet of data 20 years ago to an internet of things about 10 years ago, Industry 4.0 and so on, and now to the internet of values. And this bar chart shows the exponential growth of immaterial assets of companies in the S&P 500. And this immaterial assets is software, data, patents, trademarks, notably data, the data gold, as some newspapers headlined. This data is a crude oil or the data gold of a silicon economy. In logistics, money is therefore increasingly earned with know-how, leaderships, and information asymmetry, and not just with assets on the streets anymore. This knowledge is where the data gold lies. And it's now being expanded by Industry 4.0 and the Internet of Things via tracker systems and. Exploited by artificial intelligence, negotiated via blockchains or distributed ledger, and processed and enriched on platforms where we earn the money. This leads to our big picture in logistics and the so-called silicon economy in logistics. And let me say, it's not about something, it's really about everything. Digitization concerns production, logistics, trade, and so on. In other words, our whole life in all dimensions. And the silicon economy itself, the future is the digital ecosystems, which is a web-like and transparent connection between all actors like enterprises, people, things, and you name it, sharing a digital platform. Such an ecosystem enables seamless and dynamic connections to a variety of agents, software agents, and entities across countries and industries, physically connected by logistics operation. The basis of the big picture, therefore, of the silicon economies are the three pillars, as you see: Internet of Things, blockchain and distributed ledger, and last not least, the physical logistics, as I mentioned. If data are crude oil of silicon economy, the most decisive aspect is to keep the sovereignty about data. Trust between participants and the data sovereignty are placed at the heart of the silicon economy, therefore in the middle of our societies, deployed by initiatives like Gaia-X and its international data spaces where silicon economy is deeply connected to. Gaia-X combines the data with the use of data and the international data spaces. And this guarantees who is using the data, for how long, for which application, how many times, and according to which terms and conditions. And this is needed to realize, for example, such an application. This is a real edge application, highly decentralized, yeah, it's also a kind of swarm application. This example is the so-called ITC Pro, and the ITC Pro is a tracker for garbage cans, or better said, for recyclable containers, like paper containers or glass containers. And the technology of the ITC Pro was developed in the Renus Enterprise Lab in cooperation with the Telekom Open IoT Lab here in Dortmund in our phone over IML. And now for those who do not know Renus, Renus is one of the larger logistics companies in Europe with more than 30,000 employees and some billion euros turnover. Now, the ITC Pro is a tracker, and it's equipped with some sensors. Among others, one for the movement of the containers, and another one for the filling level of the containers via time of flight sensors, laser sensors. The rough position of the containers is measured via narrowband IoT, which is also used for the 5G compatible and bidirectional communication. In other words, ITC Pro calls it platforms once a day, or if it's required, for example, if the container is moved, then it's registered by the containers, acceleration containers, and the ITC Pro calls its platforms. And due to this ultra-low power communication and intelligent programming, the ITC Pro has a battery lifetime of more than 5 years, up to 8 years, with normal AAA batteries. This is very remarkable. This is a cellular phone which calls once a day its platform and gives its position and its filling level. At the moment, there are 120,000 of these containers in production at Telekom. Therefore, the ITC Pro, I think, is one of the largest Industry 4.0 implementations of today. Now, the ITC Pro is not just an exceptional edge device, it's also a good example of a real Industry 4.0 application. The tracker measures the filling, as I mentioned, and independently calculates when it's needed to be picked up when the container becomes full. And it also orders and books the transport in a blockchain autonomously. And that's really remarkable. Yeah? And this is done by the ITC Pro autonomously. The software, therefore, is a development in our Commerzbank. This is the third party in this project, and this is Commerzbank Enterprise Lab. And the automated payment of the container transport by microtoken was also programmed with the blockchain and in combination with the Commerzbank Lab, Enterprise Lab. Yeah, this is, as you see, a real good example of self-controlled edge devices, and including contracting and payment. And it's completely open source. Renus and their partners came to the conclusion to open this development to for all of us, as open source. Ladies and gentlemen, this example will give us some advices in direction to silicon economy. And as I think it's no longer enough for companies to focus on their core business, because their core business no longer taps into the new forms of value creation, as you saw on the slides before. No company in logistics has sufficient motivation, market power, or resources to implement the big picture of the silicon economy on its own. Not in Europe. Maybe in USA or in China, but not in Europe. Only an open, federated ecosystem of business and academia in which enabling technologies and de facto standards are developed quickly as open source is capable of laying the foundation for commercial use of AI solution with new services, technologies, and application, and enabling crucial participation and for small and medium-sized enterprises especially, as you see here on the slides. I'm convinced it's necessary to establish something like our open logistics foundation. It's time to join forces and shape the future based on open source. And I can say 2 weeks ago, the Open Logistics Foundation was founded, a clear commitment of the logistics industry to open source and European way into the silicon economy. And these are the founders of the and the board of the Open Logistics Foundation. And as you see, these are really decisive players in logistics industry, who came together I think this is the best way and a real good example to establish open source and open source community to develop our common future. Our mission is to build a European open source community to develop better solutions for digitization of logistics and supply chain management, in which all participants can realize the full value of data, and digging for the data gold together, and ensure the data sovereignty at the same time and the self-determined control of data. It's our goal to use, as you see, and create common open source APIs, smart services, components, software, but also maybe also hardware too, and build your own, and this is private, innovative business processes. Yeah? We want to do both, develop private, innovative business, new business models for the silicon economy, and create common open source APIs, the basis, the ecosystems for data sovereignty, for communication, for exchange of data, for standardization. In other words, let me say, as a Dortmund soccer fan, we should never walk alone. And this is also the headline of our Open Logistics Foundation. Let's find better solutions together, or as I said, never walk alone. Thank you very much. All the best from Dortmund.
For those who thought after the first session, well, this vision and this complexity, it's not for me, and still should wait. It's nothing as mainstream will take a long time. I think we have seen a concrete example, and that gives me maybe an opportunity for Verena to launch the poll on Slido about the question A for the second panel. What do the audience now expect? When do they expect to see real applications for distributed computing or swarm intelligence? Haven't seen the vision on the first part, but also haven't seen the first application scenario, which is really real. Would that be possible, Verena? Yeah, it's coming there.
Give me a second. I think I launched the wrong one. You need what you expect. Yeah.
Okay, so make up your mind within 3 years, within 6 years, still takes 6 to 10 years or beyond 10 years. And then I think the main message of Michael is this, the advantage of this decentralized intelligence to benefit from a coincidence on different situations, coincidence-based operations and management, particular for logistics, and particular also for the use case of garbage collection. On the other hand, where swarm may be implemented easily, or not easily, but may be implemented straightforward on homogeneous objects, the main challenge for objects is still the data collection and the data sharing, and there he has implemented quite a sophisticated architecture using DLT and IoT devices to make that happen. So now we see our audience, they are much more optimistic. Within 3 years, 50%, within 6 years, 60%, or we are close to applications and we are close to mainstream. At least there's a need from the audience for mainstreaming. And I would like to move on with that message to our next panelist, Alexandra Haas, as head of IoT solution in Swiss Telecom. welcome. She's responsible for IoT projects and for customers in Switzerland, for Swisscom and worldwide, and for E2E business customer segment. Her team supports customers from a wide range of industrial sectors in networking their machines and other assets for smart production, monitoring supply chains, as we've seen it, or construction sites, including remote monitoring and control of various applications, but also involving global public cloud architectures, working with Microsoft Azure or Amazon clouds. Alexandra, we're looking forward to your talk.
Yes, thank you for having me. Maybe a little bit unusual to have somebody from Switzerland talking today, but I was asked to give, first of all, I'm an EU citizen, so I'm very honored to also contribute with my opinion and experience in this event today. And I was asked to give the application perspective. So what is actually happening in the market, in the industries, with us, with our partners, our clients, how far is the industry in actually implementing IoT solutions and using 5G and using edge and using cloud. So, and if I see, I copy pasted it in here, the expected results of this European Commission's initiative. It's mainly about reinforcing Europe's position in the market and ensuring interoperability. I think it's a very important term to highlight here. And also from my perspective, to reduce the complexity. And if you think about who are we doing this policy for, 99% in Germany and in Switzerland, the ratio is very similar, of companies are SME companies, so small and medium enterprises. And we heard a lot of the cutting edge research before, in theory, what is happening, but for most of the companies, it's not that much about cutting edge research. They are already market leaders in their field, and they are the backbone of the EU economy. They do drive the innovation, but so far the innovation of them was not always connected with IT. So for them, it's a completely new field. And what we need to make sure is that the European Commission fosters the ability of those companies to compete internationally and to gain the new skills required, apart from their technical skills they have so far for their products, to also enable them to use IT, to use 5G, to use cloud in a way that they can compete internationally better with these new skills they need. So I've brought two real-life examples just to show you what is happening right now in the market, and using them to pinpoint on the challenges where I would like research and the help of the European Commission to focus in the future. So what would really help the 99% of the companies to actually use all these technologies to gain a competitive advantage internationally? First example I've brought you, I've put pictures, and it's always the most visual for all of us. It's a cable manufacturer, Detwiler Cabling International, one of the international market leaders here in producing cables. And they have factories, not worldwide, but not locally. They are distributed over a few countries. And what they would like to do is gain transparency, as do so many companies, of what is happening in their production sites. And first of all, now, if you talk about IoT, if you want to connect those machines, those cable producing machines, who braid cables and to who cover, who coat cables and so on, you need to operate these systems in the end. And that's actually right now one of the biggest challenges for companies, because traditionally the IT used to be the internal IT. So they provided computers and telephones and so on, but they were not responsible for providing IT for the production. You usually had a local production IT, but it's a local production IT, not an overall production IT for all the different production sites. And especially now, if you think about new business models, so IoT, maybe a sensor manufacturer who now has to connect the sensors as a service or general as a service models, the IT now has to also support the business models, not only being an internal IT, but also being IT supporting business models externally. And that is one of the biggest challenges right now. Another challenge you see here, that one of the cabling machines was connected with a gateway, is end-to-end security. So end-to-end security means that always where we do have an interface, so for example, connecting the machine to this gateway, the gateway sending the data via, for example, 4G, 5G, somewhere to the backend, to cloud. And then from this cloud, maybe to the internal IT systems where the data is actually used and analyzed. All these interfaces do have, first of all, security issues, or at least vulnerability, and authentication. I think we heard that in one of the previous sessions earlier, that authentication is also one of the biggest problems. So what we did here, and this is where we could, or we are actually making use of the hyperscalers like Microsoft and AWS nowadays, is that they do provide, in this case, we used Azure Sphere, which is which enables us to, on this edge gateway, to install hardware-based security and certificate-based authentication possibilities. And then you actually have an end-to-end security from the device over a secured connectivity solution to the cloud, and you're not as vulnerable. And most of the companies I know themselves or close competitors of them have been hacked already. So this is a really big problem for them. It's they know that this happens all around them and even to themselves. So security, an end-to-end security and an easy security, which doesn't ruin the business case of those companies, is essential. The third point is global reach. So many of our customers do have production sites internationally. So for example, in China. Right now, it is very difficult to connect these production sites wirelessly. So in general, using Internet of Things, when you have a focus on the Asian market, for example, because permanent roaming, now I'm talking from a telecom operator's point of view, is not allowed in China. So if we have we heard before from the last speaker the example with the supply chain, it was tracking of containers, I think it was. You cannot do that in China, not as simple. We have similar companies who also track their containers internationally, and you always have a problem with China. Then if you have a production site in China, it's very difficult to get the data out of there. And this should be something that the EU Commission should be aware of. Sorry. Yes, that is so far what I wanted to show here. And then the next example, now we're talking a little bit more about the really cutting edge technology, is Cloud Edge Continuum. So what does that actually mean? I'd like to show you one real life example. We asked in the last poll, how long do you think it takes for actually real examples of, I don't know what that was called, Cloud Edge Continuum or Edge Cloud. We already did that. You see that in the top left picture. This is the Microsoft Azure Stack Edge, it's called. It's the device here in the middle, this rack. It's a Tensor Core GPU where the Microsoft Azure functionalities are locally on this GPU. So you basically put the cloud on a local server. Why did we do that? You see here the example of a railway company, Cesar Rombeck. They built railways internationally, so all over Switzerland, Australia, and so on. And if you think about railway building, it's a very it's a really hard work. It's often in the night. It's also in tunnels. It's in remote areas somewhere in the outback of Australia, and they do not have connectivity in the outback of Australia, or even less so even in a tunnel in Switzerland. Not possible. So so we are using the Boston Dynamics robot there, for example, for security issues, to on the edge calculate or analyze if the workers do have their helmets on, if the workers should not step on a closed railway when they work on one rail, and on the other rail trains are actually passing. It's life-threatening to be on the wrong rail. So, the Spot actually analyzes that at the edge, but he needs connectivity for that, or at least cloud. And what we do provide, we put a 5G antenna on a rail wagon, and also the Azure Stack Edge rack, which enables us to span a local 5G network on the construction site, even in the tunnel where all the devices can connect. So talk about swarm intelligence. It's not yet swarm intelligence because they don't interoperate yet, but we are working towards that. But all the devices 5G, and then all the data can be analyzed locally in the cloud, in this Stack Edge cloud. Yeah, and then we have a bidirectional communication, so the information or the results of the analysis can be sent back to the devices. Biggest problem there right now, question was towards 5G before. 5G is available in Switzerland. We do not really see applications with network slicing yet. But the bigger problem right now is the hardware availability. So there are almost no IoT 5G devices out there yet. That is one problem. Then another problem is Microsoft also, apart from this very fancy and very, very expensive Azure Stack Edge core, you can also deploy Azure functionalities, for example, on an edge camera. It's called Azure Percept. It's, I think, for maybe 5 or 6 months, this functionality is available so that you can deploy Azure functionalities, for example, on a camera. And also there, the hyperscalers, also Microsoft, they are not hardware manufacturers. So we would now need companies like camera manufacturers or sensor manufacturers to step up and manufacture devices which support, for example, Azure Percept or other edge functionalities or edge platforms from other providers. And this right now is a really big problem, the hardware availability there. And then the last point I would like to make is campus networks. We do not really have that in Switzerland, not just to compare EU and Switzerland. For example, in Germany, we have a dedicated bandwidth available, or spectrum available for non-telco operators. So, for example, for the railway, or for campus networks that, for example, I don't know, the Siemens production site has its own campus network, and they don't have to buy this via a telco operator, but they can get bandwidth themselves. In Switzerland, this is different. You can only get bandwidth via a telco operator. This might seem, where there are pros and cons. This means all the companies, like, for example, Cesar Rombeck, have to go, for example, via Swisscom to actually get a mobile private network, like here with the 5G antenna. On the other hand, this ensures that the broader spectrum is available for everyone, and the network stability is better, because if you exclude certain bandwidth from the public operators, the network in total, the coverage and so on, of course, suffers in the reliability. So, yeah, where are we going? I don't really know. We are already really far, but we need to consider that this is the most important. Most of the companies are small and medium enterprises. So for them, it's about how can they easily use all these tools. They don't want the cutting edge. They are still just, they want to use connected sensors, for example, or connect their machines. And this is a big struggle. So in my opinion, the research should focus on how to make it more accessible for small and medium enterprises, and how to make it more, how to make it cheaper, because for them, the business case needs to work. Only really big companies can afford to invest in a business case that doesn't work yet, but maybe works in 10 years. But the small and medium enterprises, they need to make a business case working right now. Thank you very much.
Honest talk about where we are, particularly for companies and SMEs and tools. If you want to invest in sort of IoT and data, what to do with the data, it's quite clear that the hyperscalers offer a quick and easy management of data, and where telecom has a clear role about providing the connectivity and the, I would say, a bouquet of tools for helping the particular SMEs to cope with the challenges. We've seen as an alternative approach in the first talk that also where telecom was involved in setting up a DLT network, which is a higher layer of complexity already, and then where companies need to invest more in order to understand the complexity and to where the barrier is a bit higher. So here I think we know the problem space. Thank you for explaining that to us. And that's a dilemma we have, or that's a challenge we have. And I look forward to our next speaker, looking again, from a different angle. Also for automotive, at least for the connected car, it's an issue to take the easy one, in order to be pragmatic and rely on partnerships with hyperscalers, because somehow you need quick solutions. But maybe Thomas Bandover has also another view from the industrial side, production side, because TT Tech has both hats on for connected cars as well for connected industrial sites. So Thomas is a member of the executive board of TT Tech Industrial Automation, and TT Tech of computing and connectivity solutions in the industrial domain that help customers to modernize their automation systems and become IoT leaders. The company is part of the TT Tech group. As said, they have both arms, connected driving as well as industrial IoT and manufacturing. So Thomas, the floor is yours. Thank you.
Thomas is not back yet. He had
to around?
But he will join. He said he will rejoin due to our delay. I don't see him at the moment, so maybe he will come back. They told me he will come back, so maybe quickly and move to Hayden, yeah? Okay,
you move to Hayden then. Hayden has an extensive expertise as a senior industrial research and development expert. Where he was busy in flight control systems for more than 20 years, space programs and signal processing applications. So baseline technology, signal processing, sensors, integrating sensors for leading companies. For more than 10 years, he was with Rolls-Royce as a program manager. Currently, he has founded his own company, he's being managing director and owner of Think Group, of companies, but we worked with him quite on various instances, and we're looking forward to have your inspiring views on the application side. Hi.
Right, okay, thank you, Rolf. Hopefully you can hear me. So I'm going to talk about some of the applications which we're working on, and also the need really for trustworthy systems. And it sort of leads on a bit from what we've just said a moment ago about SMEs, because we're an SME, one of the 99%, and we struggle with many of the things which we've heard about. So the sort of applications we work on are things like wireless sensors for Formula One. We work on remote applications and monitoring out in the jungles of Mexico. We also look at vibration monitoring, self-powered vibration monitoring systems for nuclear power plants, for coolant pumps. We also do quite a bit of work on autonomous vehicles, and we operate vehicles in the oceans, these wave gliders you can see in the bottom of the screen there, which go around for about a year by themselves, sending data about the oceans. And we also have quite a lot going on in the smart agriculture area, and we also do other things as well. And the thing I really wanted to highlight was that in all of the applications we have, we never really send raw data anyway. We're always doing something to the data. So there's always been a degree of edge processing, but actually the amount of processing we're doing at the edge is really going up at the moment, because we can see all sorts of things which we can do. And there's a variety of things which are driving this as well. Now, if you look at what we're interested in as a company, we're interested in the performance of systems, the connectivity. We're always trying to get data from A to B in some way, and also the power consumption, because we tend to be operating on batteries or from energy harvesting. So power is one of the big issues for us as a company. When you get to the customers, they've got a different perspective on things. They're just interested in the cost of the system and the data, and they're interested in the latency of the data, the accuracy of the data, and the security of the data. And I suppose this leads into why the hyperscalers are very good at the data side of things. They're not good at the application side of things. So they're very good at dealing with one side of the equation, but not the sort of things which as a company we're involved with, which is all the performance, connectivity and power issues and the applications side of things. Now, the interesting thing is that for us, the customer really just needs to trust us, because what they tend to see is a screen with some data on, or maybe a dashboard on with some information on. And our key job is really to hide the complexity from the customer of all the stuff we're doing behind the scenes, just to provide the data that they want. Now, as we move into things like smart agriculture, we're doing a lot of things. We're doing processing at the edge, but we're also doing some analytics in the cloud as well. And one of the big issues there is actually federation. It's actually linking in with other people's systems. So we link in with fertilizer companies, for instance. So we provide data into them so that they can schedule deliveries to people. And there we're sort of linking in with farm management information systems. So farmers these days have localized systems where they connect in lots of different data sources to actually manage very, very complicated farm systems. And the key thing really is that the farmer wants control over the data, because there's a lot of confidential information in there. And they're also very concerned about being watched by the companies who are providing the sensor technologies, and also by government, because of course they can be fined as well for various things. And the other thing is that we have sensors in very remote locations. So we have quite a high or a huge attack surface where people can actually break into our systems or actually vandalize the systems. Now, as I mentioned, the amount of processing we're doing is really going up. And one of the areas where we are working is in looking at swarms of UAVs for actually monitoring forest fires. So there are big issues with climate change, and we're seeing more and more forest fires around the world at the moment. So we've actually been looking at using AI for detecting smoke and flames, using things like convolution neural networks. And we're beginning to see that AI is really becoming a bit of a driver in this area. And I wanted to highlight a particular application we're working on, which we've been working on for some time now, which highlights some very interesting liability and privacy issues, which are barriers to implementation. So we've been looking at an autonomous shark alerting system in Australia. Now, this is quite a big issue. Actually, someone was killed last week by sharks in Australia, so it is a very ongoing problem. And at the moment, what they have is a helicopter that goes up and down the beach once every 2 hours. And the reality is it really only detects about 5% of the sharks which are out there. So it's more of a publicity exercise to make people on the beach feel that they're safe. So what we'd like to do is have something which is on station more of the time. So we're very interested in using UAVs to do that. So originally we were looking at transmitting high definition video to the lifeguard on the beach from a UAV. Now there's two issues with this. First of all, it was the power consumption of transmitting the video. Because of course these are electric UAVs, so it limits the flight time of the UAV. The other issue is, in fact, the lifeguards have a limited attention span, so they can only look at a screen for about 20 minutes before they don't spot anything anymore. So it would be quite nice if we could have an automated system to actually detect the sharks. And so we then began to look at using AI. And of course, there's many things we need to do in this system. We need autonomous operation. We're looking at inductive charging and all sorts of things. But the key thing really is, what can we do with AI to do that? So we started looking at what we could do. Obviously, top left is not what we see in reality. It would be too late if we saw something like that. What we do see is we have the UAV above the coastline looking down at the sharks, and we can actually see in the ocean there, we can actually see people being cut off by the sharks. So there's a guy at the bottom there who's quickly trying to get out of the water because the shark's in the water, and there's two people who are actually cut off by the shark. And so what we need to do with the AI is rule out people, surfboards, dolphins, floating rubbish, etc. We want to be able to identify the shark and the species of the shark, because certain sharks are more dangerous than others. So we've got great whites, tiger sharks and bull sharks are the key killers. We want to be able to track the sharks But the other thing we want to be able to do is identify aggressive behavior as well. So the way the shark swims is very important, because most of the time sharks are not actually aggressive. It's only when they're aggressive that we need to worry. Now, as a company, of course, our issues are the power consumption again. So we're trying to do things on a Jetson Nano, and it's the power we need to do the algorithm at the edge. However, the barriers to actual implementation are twofold. One of them is privacy. So we're operating over beaches, and of course, people don't like to have cameras operating over beaches. So you can imagine a swarm of UAVs with cameras looking down at the beach. People don't like that. And the other problem is what happens if we don't detect the shark? Because liability then becomes a bit of an issue for us as a company. And literally, it could bite your arm off from a liability point of view. So trust is one of the key things that we need for the future, and it depends on many, many different attributes. So we need to worry about how we deal with data. So how do we collect data? How do we get rid of data? How do we inform people about what we're doing? We need to think about the trustworthiness of the AI, because we need to make sure that we actually detect the sharks to a reasonable level of accuracy. The system as a whole needs to be trustworthy, because it needs to be on station, it needs to be resilient, it needs to be out there all the time, looking for the problems. And then liability is the key thing for us as a company, is that we need to be able to prove that we've done as much as possible to make sure that we've done everything reasonable to make sure that the system works correctly. And that is a big challenge for systems like this. Now, the other thing I wanted to highlight was the problem of ubiquitous intermittent connectivity. So people have already mentioned 5G and various connectivity. We have many applications in Australia and also all around the world. And one of the big issues is that currently about 90% of the Earth's surface doesn't have any mobile phone or Wi-Fi connectivity. And even with 5G connectivity, it's not going to be all around the world. And so we need some sort of connectivity for our very remote applications. We can think about autonomous cars, UAVs, smart farming, remote monitoring. All of these things need that connectivity. Now, there's a lot of things going on with swarm satellite constellations at the moment. There are 7 different competing companies all trying to create the internet coming from the satellites at the moment. So we're actually working with one of those companies to try and work out how we can exploit it as well. And the big issue at the moment is that we're using low Earth orbit satellites. So these things go around the Earth and they're not on station all of the time. So this means that we get intermittent connectivity. So we get ubiquitous connectivity, but it's intermittent. So we get 15 minutes of connectivity and then it disappears. Then we get another 10 minutes. Then we might get another 20 minutes of connectivity. So this clearly means that we need to have systems which can operate autonomously in the future. So there always needs to be a degree of autonomous operation. So this leads us to where we think we're going with the future. So we're looking at decentralized intelligence and local data sharing in future systems. So if we go from the right-hand side of this picture to the left-hand side, we can see that one of the issues for us is that we can't really do real-time control, feedback control loops to assets which are out in the field. So we might have our UAVs, we might have remote vehicles, we might have sensors, etc. So we can't do real-time control because of the latency through the system. Going the other way, we can't transfer huge amounts of data because transferring data costs lots of money. So if we send an image over a satellite, if we're sending images every day over a satellite, it will cost you thousands of euros a month just in the cost of sending those images. So that's not something which companies are prepared to pay for. And the other issue is energy. And energy is one of the prime things which drives us as a company. Are very important for the future, so we need to keep the data local as much as possible. And so things are naturally going to move you towards decentralized control and swarm intelligence. It's the way it has to move, really. So we can see that we're going to have autonomous groups of platforms out in the field, and we really need secure clusters of edge devices. So we're going to have different systems talking to each other at a local level. It may not be everything talking to each other, but they'll be working in clusters together to actually provide different functionalities. So to wind this up, what we're seeing is the level of smartness is increasing dramatically in sensors and edge devices. And we're getting into issues of, well, what do we do at the edge and what do we do in the cloud at the moment? And we're sort of discussing this. And a lot of it is driven by cost, the amount of data we need to transfer. Complexity is a big issue for the future. We know we need autonomous operation for the future. We need distributed control. We need distributed information processing. We've got all sorts of things like machine learning coming in there. Obviously, these systems are going to fail. Dynamic reconfiguration, because it's going to be inevitable that things are going to fail. And also these systems are going to grow. So we need composability and scalability for these systems as well. Now, very interestingly, talk about data, and data had been the gold. Well, data is the new oil, but we don't want leaks in that data. So we need to consider the privacy and security issues of that. And actually moving to the edge solves many of these things, but we really need these secure edge computing clusters. And the other thing we're seeing is multi-tenancy from competitors. So we're actually seeing other people's software on the same devices, and we're going to get worried about different levels of application criticality on those devices. Security is a big issue, and this has been mentioned already. As we move to more remote distribution of sensors and assets, we see a huge attack surface. And we can see many ways of actually breaking into this, things like node replication. We can see routing attacks being an issue. And one of the things we worry about are distributed denial of service attacks, because of course, what you can do is bring down a whole fleet of UAVs just by draining their batteries. Federation with other trusted service providers is important for the future. And we see that we need interoperability and quality of service contracts to allow us to do that. I want to highlight the fact that edge devices are not always static, and they may be in very remote places. So we have things like the wave gliders, the UAVs and vehicles, and we need approaches that can tolerate intermittent connectivity. So we always need a degree of autonomy in these vehicles to deal with unpredictable environments, and then synchronize points to actually take the data off. And really, AI is a big driver in all of this, looking to the future for local processing, not only for things like image processing application, but also in the autonomy side of things. We really need transparency and ethical guidelines around this. And luckily, things are already moving in that way. For us, as a company, we need to prove trustworthiness. So we need to ask ourselves a number of questions. Is the system safe? Is it reliable? Is it resilient? Will it keep working? Is it secure? Because that's the only way we'll get customers to buy these systems. And the big challenge for us is that as things get more and more complicated, do we really understand how the system actually works? So that's my final slide. If you want to contact me afterwards, these are my contact details. And if you're interested in the applications, we have quite a few interesting applications which you can have a look at on our technology radar.
Okay. Much, Hayden. I think that gives another dimension, particularly, if you have a lot of images on your edge devices, that you have to avoid streaming to the central services because of the energy, because of it's getting too complicated and too complex, and because of the timing, and that grouping different systems together would increase the quality of the data, reliability of a decision, detecting a shark, detecting a disease, or detecting fires and frost. And that the swarm approach increases reliability, the trust, and relaxes eventually the requirements for learning at the edge. So that basically concludes on that discussion. I've seen that Thomas Bedlover has joined us. Sorry for the delay. I think we will take your talk now. To give another application dimension, as mentioned, you're a member of the executive board of TTTech. TTTech as a company has two legs, one of connected cars, connected driving, as well as the industrial side, where TTTech develops innovative computing connectivity solutions in the automation domains. So please, the floor is yours to provide your application view. Thomas.
Thank you very much. Yes, I had to change my location in the meantime. Hope everything is working well and you see my presentation. Thank you for the introduction. As a general manager of our company, my role today is to give you and provide you some insights on from an application level perspective, what we as a company are actually able to deploy today with our products into the industrial space. And let me start with the first example I want to share with you, which concerns the safe and reliable control of wind turbines. So what you do there is we have created a distributed architecture that comprises of a lot of different modules that are hooked together on a real-time basis with an Ethernet connectivity solution. Some of these devices are safety-oriented, functional safe control, and others are not. And the way how we designed that with individual decentralized modules lets us fit the functionality of such a turbine very well together with the number of devices that we deploy. This is one aspect, and as we grow, so to speak, the functionality, we can add additional devices. What we also can do to provide high availability, we can switch devices in parallel, and even the network can be implemented redundantly, so that we have a 24/7 operation across the year, so that every second of wind power can be harvested. That's important in terms of energy, but also in terms of cost, right? So what we have here is really a decentralized system that is also running fully autonomously on a 24/7 basis, and there is still a small hook into a substation and a SCADA system, of course, to one centrally managed link. And this is something that all these distributed systems have currently in common, that there is always one central management entity involved. The second example I want to give is what we do in the off-highway space. Here you see a snow groomer. This is one of our customers, but normally, main target market segment is the agricultural segment. There is a lot of hydraulics involved in these machines, from tractors and harvesting machines. And every time when we talk about hydraulics, there's a lot of danger also coming from these big forces of hydraulic systems. So safety control always plays a role, and especially safety control is very well implementable, so to speak, in form of decentralized control system, because you can easily decide which function should be kept safe and which one not. And you hook all these functions together with a real-time connection. So there's, again, one central system, which is the HMI that sits normally in the cockpit. And today there are also cloud connectivity solutions around. What's not implemented today, though, is the fully autonomous operation. So I would say this is in work, of course, and there's a tremendous benefit of imagine these large scale fields that you have automatically harvesting without anyone. That's a very interesting aspect, but it's not, or it's going to be reality in the next years, but it's not a standard function, so to speak. A third example is from the industrial environment. I call it the industrial asset management. Because industry started with this segment even before people started to transmit data somehow over these connections. They started to look, okay, where is my fleet? Where are my systems? What is the status of my system? So kind of a monitoring system. And that has become quite a standard solution, but it's in fact the first interconnected system that we have seen in the industrial space, where you can utilize easily all the cloud connections to just get aware where your systems are, how they are operating, equipment efficiency, and so on. And then it started more and more into a data-driven approach where these individual systems transmit a lot of specific data, and you start to evaluate this data and calculate something like a KPI out of it in the system. But this is already this data set approach. But industrial asset management is well known and widely used at the moment. Also here again, there's a centralized management system always involved that is usually cloud-based or sits on premises. to control and connect all the nodes together. What's coming at the moment with big steps, and we discussed a lot about it, and this is a picture where all of you are well aware about, that's the industrial edge computing. So with the introduction of more and more compute power in the edge layer, you see that in the middle, you're not just able to collect data, but you're also able to deploy from a central management system, deploy software to the edge components in form of binary applications on one end of the spectrum over container-based modules, or at the end of the other end of the spectrum, complete virtual machines. You can do this. You can, so to speak, reconfigure your system. You can deploy software very close to your machines, and that's the basic technology that you need to have self-modifying and also autonomous system at the end. So we are taking big steps in this direction. It's still in this early stage of development and deployment. We have customers that are on a rollout basis with such systems, but it's far away from being mainstream or usual. What we also do in our company is to provide the right amount of connectivity, specifically the real-time TSN networking underneath, because if you want to be able to control really physical energy, and yeah, that's normal use case in industry. Whenever physical energy is involved, you need to be either safe, or you need to do that in real time, and you need to have the right appropriate networking in place. So we are working on edge computing and the appropriate connectivity, and we call our platform solution NERV. This is our product that we try to deploy to customers that want to start with edge computing. So we are not going to have any application level knowledge there, but there's a lot of things to solve for someone who is a machine builder, for example. Yeah, it's first the cloud connectivity, it's the security, it's the trustworthiness that we heard about. It's the mechanisms to deploy software, it's multi-tenancy, and all these things we try to help and to provide so that people in the industry can start to implement their, well, you can call it digitalization projects, you can also call it Industry 4.0 project, whatever, but there's a lot of infrastructure that needs to be in place before you can really start. And this is what we are trying to do. I think there is a lot of technology available today, but the awareness that the customer is not that far. So we need still a lot of energy to introduce systems to the customers, to educate machine builders and factory owners how such systems are used and how they work, to get the trust. And the most important thing, to explain and look what is the value that such a system provides. It's not technology that you need to provide, it's the value that you need to provide. And if you solve these questions, then you take a big step further. One of the segments that we are working also with such a system is the energy storage, specifically hydrogen energy storage, which is normally decentralized. Again, here is a decentralized node that controls something locally, and that's steered by a management system that sits in the cloud that can do some analytics and some general control, deploying software to the edge back and forth. Yeah, I've mentioned that OPC UA and TSN, these are standard and open technologies. And it was mentioned for several times in the morning that we can only be successful on a general basis when we provide interoperability across different functions. And we as a provider of platforms are very focused on providing open standards, open interfaces, open protocols to allow users and applications to connect well together on a standard basis. Otherwise, you get these silos and the systems might not be successful over time. OPC UA is one of these protocols well accepted already, and we see that widely adopted already across the industrial space. PLCs, edge computers, industrial PC, everyone is now OPC UA aware already. So that's working very, very well. Now let me quickly come to the conclusion. So what I wanted to show is that decentralized architectures are widely accepted and usual. So that's full check mark. Why? They provide, so this decentralized approach provides modularity and reduces the complexity, specifically when it comes to safe systems. Growing the functionality of a decentralized system also means adding additional nodes or services, depending on the distinct meaning behind these terms. So you can have larger or smaller systems very easily. Yes, always some centralized management will be involved, normally in the cloud or on premises. That's still present and will be present in future. I don't think about the fully decentralized without any steering intelligence. I think that will not become reality. While in edge computing, I cannot say it often enough, is of course one of the key technologies that we need to apply this decentralized autonomous intelligence in the field. There's no way around. That's the technology of today to operate factories like a data center, having full orchestration behind. But these are, you know, IT heavy mechanisms that are not so well understood on the OT space. And this is where we need to be careful. And it's our job at TTTech to explain what it is, to provide systems, and to allow this technology to be deployed to the OT space. Yeah, fully autonomous operation, partially implemented, partially not. At specific areas, we see full implementation, but autonomous operation is still something that needs to come. In most of the fields, in big steps, you know, autonomous car driving, there's a lot of engineering and research ongoing, but we have still a long way to go in autonomous systems. Thank you.
Rolf?
Very little time for questions, but I would pick up one question from the audience, which is recurring. We've seen in Heiden's presentation that there's a need to avoid large streaming of pictures to the cloud services and to keep data local in order to have reaffirmation of decision making. We have seen from the presentation from Thomas that cloud integration is essential for remote asset management for complex devices like a windmill or for autonomous operation of systems, but also for industrial asset management. Although there's a lot of conservative reaction attitude still in the manufacturing industry, putting their data into the cloud services. So, and also it was mentioned that cloud offers a lot of opportunities to dynamically managing systems via containers, via virtualization and deployment of software. But still there's a long way to go to educate the machine builders in order to accept such a dynamic solution. So my question is, to what extent, you know, Europe has, I think if cloud is essential still in many of the applications, has the capacity to have its own cloud services and infrastructure, or to what extent, you know, from partnership with the existing hyperscalers, which was mentioned in the chat. So is the approach of the hyperscalers already so advanced that the benefit is higher to rely on their cloud services, or what is the identity of the European companies? And Thomas, maybe you start.
Yeah, accidentally. I'm sorry, I suddenly dropped out, so I missed the later part of your question.
Well, the question is, I think you nicely illustrated, the role of the cloud to have sophisticated services for remote asset management, but also for autonomous operation, and for reconfigure and dynamic system operations for industrial systems, and to what extent, these cloud services, are provided, by yourself, by the same company, or you rely on external services, or to what extent do we have the benefit to rely on existing services from hyperscalers who have developed many of the applications, as we heard from Alexander?
Yeah. So there is, this is we call it software-defined systems that we try to introduce, and the software is a big variety of offers that you have today. So first of all, we don't mandate any specific cloud vendor. So the user is fully free and open, and normally has chosen his cloud provider, and edge computing systems can work with all of the cloud providers. This is there's a big degree of openness from that side. Some customers tend to be very conservative and try to keep everything on site still, specifically when it comes to data and ownership of data. At least 50%, I would say, are very careful and asking the question, okay, who has ownership? The other half is more open to cloud concepts and trust already into the cloud space and say, okay, this is my area. No one will steal my data from there. And software-wise, what we do is we try to stay very open. So it's like a smartphone, which just provides an Android system and nothing more. And it provides a means where everyone can come in, the user itself, his knowledge on applications and system integrator, hyperscaler with, I don't know, IoT edge or other mechanisms. All things can come together on such a platform and put the software models on that in form of applications, containers, or virtual machines. So I think that at the moment that works well. The question is more, how can we design such systems in the sense of the customer that it creates value? So this is sometimes a learning process. People start with collecting data and find out how to calculate KPIs out of that after half of a year. When they start to reduce data flow to the cloud by deploying back to the edge some calculation mechanism that runs locally with less latency and more compute power there. So this is always a journey, and it starts with data collection and ends with a software-defined industrial systems that is very similar to the way how we operate data centers today, but of course to a much smaller extent. So.
Good. To be short, you're favoring an Android, basically open system for the edge to provide the dynamics and be open, and you believe that the edge is cloud agnostic. Alexander, would you agree to that proposal or that? Alexander has left.
To leave at 1.
Maybe Hayden, for you.
Yeah, I think it's interesting because increasingly people talk to us about they're worried about the confidentiality of the data, and factory owners in particular are worried about keeping the data on site. They don't want to share it with anyone because it's commercial confidentiality. And we find the same thing in the farming domain, where the farmers are getting increasingly worried about what data are they sharing with people. And it comes down to one of cost again, because if you want to manage your own data, you have to put in the cost of doing that, and you have to get skilled data professionals to actually manage all of this data. And when you start looking at the costs of doing that, that's when people start thinking, well, actually, maybe I shift it to a external service provider. And this is something where I think the question is really, what data is it you want to keep local, and what is it you're prepared to share with people? And when you start looking at the data, it's difficult to understand what is really truly commercially sensitive. There's many things which you can record from machinery, which is not that commercially sensitive and you can't get much from it. But there are other things which are very important. So it's trying to understand which data should you process locally and which data should you move to the cloud, and try and minimize the management that you need to do. And I think the opportunity is actually to move more of it into local edge clusters to actually deal with some of that. And this is why I talk about trusted edge clusters, because I think that's something where I think there's an opportunity for Europe to actually provide these. And then, of course, data will go off to the large hyperscalers, but the hyperscalers really don't understand the application side of things. And whether it's worth their while investing the money and effort actually getting into those markets is another question.
Okay, last word also to Pushottam. What do you think about the idea of favoring an open OS and Android for the edge and to be cloud agnostic? Does it make sense?
Yeah, it does. And that is where it will drive standardization, and that is where this heterogeneous edge devices, where we would be able to do service orchestration and stuff like that. So definitely that could be, that is a good idea for sure.
Okay, Jake, last word from your side. What do you think about the Android for the edge in the industrial manufacturing domain? Is that feasible, or is that a reliable vision? Maybe he's not yet there. Maybe Mark, are you still available? No, it's not available then. With that, I think last thinking in your mind, I'm closing the panel. Pretty sorry for you for a bit of delay. Thank you very much for your input, for your presentation, for your contributions and the discussion. Apologize again that the discussion felt a bit short, but I think we touched on the main points. And thanks again, and I'm closing the morning.